Assalamu alaikum. Hi everyone. Can you please help me? Is my voice clear?
Yes, sir.
Okay, thank you so much. We are waiting for our participants. We have few more. So please wait another 1 or 2 minutes. I am texting them. So we will start shortly. Thank you. Yeah, doctor, is everything okay there?
Hello.
Um,
Yes, from my side is okay.
okay, doctor, thank you. So, I think we can start. Please wait another 1 minute. So we'll start by 10:05. Now 3. So we'll start at 10:05.
Ni apa nama dia? Ni bukan, ni host. Dia yang host dia universiti apa? Dia UPM. Sebab aku ada je group Telegram kan. Mostly program kat situ UPM.
Okay, so I think we can start. So first of all, I'd like to say thank you everyone for taking time and your efforts and money to join with us today. I hope you will learn a lot about Matlab and optimization. So before I pass the microphone to our speakers, let's introduce him to you. Dr. Prem Kumar has PhD degree from Anna University, Chennai, India. He worked in various reputed institutions in India and has more than 14 years of experience. Currently, he is working as an associate professor with the Dayananda Sagar College of Engineering, Bengaluru, Karnataka, India. He has published over 100 technical articles in various national and international peer-reviewed reputed journals of IEEE, Elsevier, Springer, IET, Wiley, Taylor, and Francis, etc. With over 1,500 citations and an H-index of 20. He is listed in the top 2% of scientists worldwide during 2021 to 2022. Based on a study by Stanford University, his current research interests include power converters, inverters, renewable energy systems, smart grid and microgrids, PV parameter extractions, modern PV, MPPT, PV array faults, non-isolated or isolated DC to DC converters for renewable energy systems and electric vehicles, BMS for electric vehicles, and optimization algorithms, including single, multi-objective, and many objectives for real-time power electronics and power systems problems. He is an editor or reviewer for leading journals of IEEE, IET, Elsevier, Wiley, Taylor's and Francis, Springer's, MDPI, iOS Space, Tech Science Space, etc. He has also written 3 textbooks titled Linear Integrated Circuits, Electrical Machines 1, and Artificial Intelligence and Intelligent Systems for Beginners. He has published and granted 8 patents by IPR India and IPR Australia. He is an active speaker and has delivered more than 15 guest lectures at various organizations. He has received various awards and rewards for his outstanding contributions to teaching and research. He is a member of various professional bodies such as IEEE, ISTE, and IAENG. So I'll not take much of the time. So directly I will welcome our speakers. And before that, when you are not talking, please make sure that your microphone is mute. And if you want to talk, at that time you can unmute. So thank you so much. So over to you, Doctor.
Yes, thank you, Mohammed Zahar Islam, for introducing me before starting my session. So I just share my screen first, just to confirm it if it is visible to you. Is it visible?
Yes, Doctor, it's visible.
Yeah, thank you. So, very good morning to all. First of all, I would like to welcome you all for this wonderful one-day workshop on Matlab and Optimization. And I would like to thank Mr. Mohammed Zahar Islam for providing this opportunity to discuss with you people in association with Education and Research Desk Malaysia. In today's topic, in today's discussion, I'll be talking about optimization algorithms applied to real-world engineering problem. So I myself, Dr. Prem Kumar from Dayananda Sagar College of Engineering, India. So in today's discussions, what are the things I'll be covering is, first I'll be talking about why optimization algorithms are required. What is optimization algorithms? And why it is required, then how to formulate optimization problems. Okay, so that I'll be discussing. And after that, what are the different classifications that are available in the optimization algorithms? Okay, and I'll be talking about the most famous and most preferred optimization algorithm throughout the world is particle swarm optimization algorithm. So I'll be giving you a hands-on training how to develop a simple particle swarm optimization algorithm. And we'll be analyzing the exploration and exploitation of the PSO just by changing the parameters of the particle swarm optimization. And again, the second algorithm, I'll be taking the Gray Wolf optimizer. So this is also one of the famous algorithms throughout the world. Okay, and we'll be formulating both the algorithms, and we'll be validating the algorithm with simple numerical problems, as well as for today's discussion, the real world problem, what I have taken is the parameter estimation of the photovoltaic cell by using the both algorithms, what we are going to develop it. Okay, so this is my overall agenda. Okay. So if you have any doubts in between, you can ask me, or else at the end of the session also you can ask me. Okay. So it's purely, I can say the half of the session will be on the theoretical discussion, then half of the session will be on the practical side. I hope everyone is having your laptop with you with Matlab tool. So if it is there, it is easy for you to have a hands-on, or else yes, you can listen it. You can later you can try it on your own. Okay, so I just wish you all a very happy learning. Yes, so first let me start the first session, or the first topic. What is optimization? Okay, so few people are familiar about optimization. So what is optimization? So a few may not be knowing it. Okay, so for them I think it will be very useful. So what is optimization? So I can say it is making things better. So I have certain things. Okay, I just want to run a business. So as everyone knows that if our business, the ultimate aim is the profit, right? So I just want to get more profit with less expenditure, so that I can say it is a simple optimization problem. So making things better and generating more profit, as I said. Yes, so determining the best. Okay, so I have around 30 to 40 students in a class. So in that, I just want to pick best person. Okay, so that is also an optimization problem. Yes, and do more with less effort. Okay, so expecting more work with the less effort. Okay, so that's also an optimization. So these are all a simple the keywords for the optimization, I can say. And as per the book definition, okay, we can say it is nothing but a determination of the values for the design variables. Okay, the design variables, we can say, or the control variables, or the decision vectors, we can say. So we are going to find the values of these decision vectors or the design variable by minimizing or the maximizing the objective. Okay, and also it has to satisfy the constraints. Okay, so we have set of design variables. Okay, we'll be having a set of bounds for each and every variable, and we'll be formulating the objective function, and we may minimize the objective function, or we may maximize the objective function by adjusting or by computing the design variables. Okay, at the same time, it has to satisfy all the constraints. Okay, so this is what the book definition. So I hope you people understand what is an optimization. So still, if you want, if you have a doubt, okay, you can look at the structure, you can easily understand, okay, what is that optimization. So for all the optimization problem, so the first and foremost thing is, the objective function. Okay, so that's what you can see the min of j of x comma p, so that you can observe it is what your objective function. Okay, for any problem you can take any of the problems. So for all the problems, first thing what you have to do is you have to formulate an objective function. Okay, so the objective may be a minimization objective, or it may be a maximization objective. That depends upon the user. Okay, the next one, after formulating the objective, you have to check, is the problem what I'm going to solve, is it having any constraints? Okay, so the constraints, as it is again classified into two types. We can say it's an equality constraint and inequality constraint that you can observe here. The G is less than or equal to 0. So I can say this is called inequality constraint. And the H is equal to 0. You can see it is an equality constraint. So some problems will have the equality constraint, and some problem will have inequality constraints. For example, if you take a power system problem, maybe you have so many power system problems like optimal power flow, economic load dispatch. Okay, so many problems are there, right? So if you take those problems, the number of constraints are more than 100. Okay, more than 100 constraints are there. So when you solve the problem, so your algorithm has to handle this 100 constraints. Okay, so yes, obviously for all the real world problems, so you'll be having a constraints. Then after the constraints, yes, in the previous slide, what I told you is we'll be having a decision variable or design variables. So when we have a decision variable or design variables, we have to define the bounds or the limits for each and every variable. Okay, so here you can see the bounds are given. Okay, so there'll be a lower limit and there'll be upper limit. Okay, for each and every variable, we have to define the lower limit and the upper limit. So once you define everything, yes, now your problem is ready to solve by in any algorithm. Okay, still if you have a doubts, yes, you can take this simple picture so that you can easily understand what is an optimization problem. So here you can see the two persons are standing, and this person is asking this person to move towards the target. So the flag is the target. Okay, it is on the mountain. Okay, this person is asking to this person to go to the flag, and you just touch it and come. So this is what the objective. So here I can say the objective is go to the target. Okay, and here you can see that obviously the objective is what is a minimization, right? So with a minimum distance, I have to walk. Okay, I can run, I can walk. Okay, whatever you can do. Okay, with minimum time and with minimum distance, I have to reach the target. So that is what the ultimate aim, or you can say the objective. Okay, and now here you see that this person can reach this target in any of the way. Okay, so he can go in a zigzag way. Yes, he can go directly. Okay, or he can go, yes, he can go like a spiral. Okay, he can reach the target. Okay, he is having a lot of options to reach the target. Okay, but what this fellow is telling is, no, you should not walk toward the mountain. Okay, so here this is what your bounds. Okay, this is what your limitations. Okay, within this limitations, within this boundary, you have to reach the target. Okay, this is what we call it as a bounds. Okay, so the objective is you have to reach the target with less time and the less distance. Okay, and this is what the bounds. This is what the bounds. And here you may ask, what is the constraints? The constraints may be the environmental conditions, maybe it is health conditions, or whatever it may be. Okay, so suppose if it is suddenly raining, or if it is suddenly hot. Okay, so those are all the constraints, right? So we cannot predict everything. So we'll be having the constraints. So this person has to meet those constraints, and he has to reach the target. Okay, this is what a simple optimization problem I can say. Okay. Yes, so now you see for an optimization problem, what are the things are required? You can see that this is what is your simple system. Okay, for this system, you'll be having a number of inputs. Okay, and you'll be having the outputs. Output is nothing but your objective. Okay, and here you can see that there are a lot of constraints. There are a lot of constraints, and you can see my wish is to minimize this function because I'll be formulating the objective function. I'll be minimizing it by satisfying the constraints. Okay, this is how the typical optimization problem looks. Okay, and here, what is the role of the algorithm? Okay, that's what we should know. Okay, so here you can see this optimizer is nothing but your algorithm. Okay, so what this optimizer will do? Yes, so this optimizer will take an objective. Okay, it will take an objective, it will solve the objective. Okay, and it will change, or it will compute the input variables. You can see it will compute the input variable, and it will be given to the system. Okay, and when it is computing, it will take the constraints. As I told you already, the constraints may be a equality constraint or inequality constraint. So just by taking an objective, by considering the constraints, yes, it will be computing, or it will be optimizing the design variables or the input variables, and that will be given to the system. So this is where the role of the optimization algorithm. Okay, I hope you understand. Yes, so let me move on to the next slide. So yes, so this is one simple example. Or we can say designing a table. Okay, so here I can say my objective is to minimize the weight of the table. Okay, and for the table, I have given the length and width of the table, so it can vary from 2 meters to 7 meters length, and it can vary, the width can vary from 2 meters to 7 meters. Okay, this is what the constraints is given. Okay, and here you can see that the minimization function is taken. As I told you, first we have to formulate the objective function. So here my objective function is 1 into length plus width. Okay, this is what my objective function. Okay, so I just want to create a table. Okay, so that I need to the table with less weight. That is my objective. Okay, so this is a very simple problem, because by seeing this problem, by seeing this formulation, you can easily tell what will be the value of length and what will be the value of width for the less weight. Yes, obviously, if the length and width is equal to 2, yes, obviously you can have a table with less weight. Okay, but this problem looks like a very simple problem, right? So this problem looks like a simple problem. Yes, so but if you take any kind of real world problems, no, so the objective will be, sometimes it will be a linear equation, sometimes it will be a non-linear equations, okay, and the constraints will be more constraints will be there, okay, as I told, even our OPF problem is having more than 100 constraints, okay. For those kind of difficult problems, you cannot easily find what will be the bounds of the what will be the actual variables of the design variables. Okay, so just to have a small understanding, I kept this example, but this is not all, the problem is not always a simple problem. Okay, so for the real world problems, it will be very difficult to solve with simple algorithms. Okay, yes. So now I'll just go to the classifications of algorithms. Okay, the first classification is exact algorithms. Okay, so this is what the in general they have the exact algorithms, like the deterministic algorithm, iterative algorithms, the brute force algorithm. So many exact algorithms are available. Okay, so this exact algorithms, what it will do is it will guarantee 100% accurate result. Okay, so these exact algorithms will guarantee 100% accurate result, but the problem is it will take more time to compute the variables. Okay, so that's a problem with the exact variables. So it will give the better result, but it will take more time to solve the problem. Okay, so for example, if you run the OPF problem, it will take days of time to give the best result, but definitely 100% sure it will give the best result. So but we cannot wait for more time to get the best results, right? So we need a result within short period of time, right? So for that purpose, we have the heuristic algorithms. Okay, the heuristic algorithms is completely depends upon the random nature of the random nature. So it's a kind of a stochastic algorithm, we can say. So this algorithm, yes, it will give the solution, but the solution may be near accurate solution. I cannot say it is a complete 100% optimal result. Okay, it will give the nearby solution, but it will give the solution very quickly because of the stochastic nature. Okay, so I can say simply, in general, we have exact algorithms and heuristic algorithms, but in today's session, I'm going to talk only about the heuristic algorithms. Okay, so means it will give the quick results with maybe near optimal results. Okay, yes, so one simple example, what is heuristic and what is exact algorithm is. So we have a two-person, Jennifer and Bob is there. Okay, so what we have given a book to both of the people. Okay, so they have an exam. Okay, they have an exam. Maybe we have given 1 month time to prepare. Okay, so what the Jennifer will do is she will study throughout the month. Okay, and he could able to get 100% of the result. You can see. So she read everything and she memorizes all the pages of the book and she has written the exam very well. Yes, you can see the result is 100%. Okay, but if you see the Bob, what the Bob is doing is the Bob is getting some kind of recommendation from his seniors. Okay, what are the things need to be read from the book? Okay, so he just spent 1 or 2 days for the exam. Okay, and he just memorized few pages recommended by his seniors. Okay, yes, you can see that the person could able to get 60% of the marks. Okay, see that here Jennifer read 1 month and Bob read only 1 day. So the Jennifer got 100% mark and the Bob got 60% of marks. Now the scenario is different. What the scenario is, I'm giving only 5 days. Okay, I'm not going to give 1 month. Okay, I'll be giving only 5 days. Okay, so in this case, what will happen? And the Jennifer needs 1 month to prepare, right? So the time is very limited. Obviously, she cannot read all the pages. But you know what the Bob will do? Bob will prepare, whatever the pages recommended by seniors, he will prepare only that. You can see that the results produced by the Jennifer and the Bob. So Jennifer could able to read only very few pages, so she could able to get only 20% of the marks. But the Bob, again, he got 60% of the marks. So this is what one simple example to understand what is the exact algorithms and what is the heuristic algorithms are. Yes. So I hope you can understand what is exact and what is heuristic algorithms. Okay, so now you can see a few more examples in each class. So in exact methods, the very famous algorithms are the gradient descent methods, okay, the brute force search methods. Okay, in both the methods, the gradients are required. The slope of the problem is required. If the slope of the problem is not there, these methods fail to find the best results. Okay, but you see the heuristic methods, we have so many thousands and thousands of heuristic algorithms are available. Okay, I just listed very, very few algorithms. You can see the hill climbing, simulated annealing, ant colony, genetic algorithm, differential evolutionary algorithm, particle swarm optimization algorithm, artificial bee colony, gray wolf optimizers, so whatnot. So many thousands of heuristics algorithms are available. Right. So, but for today's discussion, what I'm going to do is I'll be taking only particle swarm optimization and gray wolf optimization for our discussion. Okay, so here one more question comes. So what is the question is, the few people are, they confused with the heuristic and meta-heuristic algorithm, right? So what is heuristic and what is meta-heuristic algorithm? So the heuristic algorithms are problem-dependent algorithm. Okay, it means that algorithm is suitable only for that particular problem. So in that case, we can say that algorithm is a heuristic algorithm. Okay, for example, you can see the ant colony optimization is not preferable for all the problems. It is mostly preferable for combinatorial problems. Okay, so it is a problem specific. Okay, but the meta-heuristic algorithms are not like that. Okay, the meta-heuristic problems are, it is a kind of a black box. You can use it for any kind of problems. Okay, so this is what a simple difference between a heuristic and meta-heuristic algorithms. Okay, I hope you understand. Yes, I'll just move on to the pros and cons of the deterministic and stochastic, or you can say the heuristic algorithms. Okay, as I told you already, you see the first one in the exact algorithm. The very first example is the gradient descent method. Okay, just hold on a second. Yes, you can see that the gradient descent algorithm. Okay, so this problem is having the minima here. It's what the global minimum point. Okay, you just see this algorithm looks for the slope to find the problem. Okay, if the problem is not having the slope, okay, it cannot find the proper solution. Okay, but you can see that this is the stochastic algorithm. You see the stochastic algorithm, you see my populations are moving randomly throughout the places, and finally it could able to reach the global value. Okay, so suppose if the initial solution, for example, here I have taken the initial solution, quickly it reaches the global value. But for example, if I take the initial solution here, since here you can see that there is no slope here, so it may be trapped to the local optima. Okay, but if you see the stochastic algorithm, it will find the solution randomly. It will move throughout the search space, and finally it could able to find the global optima. So this is what a simple example for deterministic and stochastic algorithm. So if we take the exact algorithm, okay, the exact algorithms are very efficient for the unimodal problems. What is a unimodal problem is, if the problem is having only one global solution, okay, then we call it as a unimodal solution. Okay, so you just take these problems, you can see that, it is having only one global solution. So for these kind of problems, this exact algorithm or deterministic algorithms are very better algorithms. Okay, but if the problem has multimodal feature, okay, for example, it is like this, the problem like this, you can see that there are a lot of local peaks and global peaks are available, right? So this is called a multimodal problem. Okay, in this multimodal problem, okay, yes, the deterministic algorithms are not efficient. It will be trapped by the local optima. Okay, so for this kind of problem, because as I told you, it's highly depends upon the starting point. Okay, if the starting point is taken somewhere, yes, obviously it cannot find the global value. Okay, but for this kind of problems, what algorithms are suitable? As I told you, yes, stochastic algorithms are the best solution. Okay, so that because it's having the random component, so it will find the solution randomly throughout the iteration, and finally it could able to find the global solutions. Okay, yes. So this is what a simple examples of pros and cons also I have told you. Okay, so now still I could see some differences between the stochastic and deterministic algorithm. So I can say simply to say, yes, the deterministic algorithms are having, the local optima trap is there, okay, and it takes more time, okay, as I told, it requires a gradient or the slopes to find the solution, okay. But you see that your deterministic algorithm having few advantages also, as I told, it is reliable. For example, I'm running the algorithm, it is giving one solution. If I run the algorithm for 30 times, for 30 times it will give the same solution. Okay, that is an advantage of the deterministic algorithm. So we can say it is a reliable algorithm and it requires only few function evaluation. Okay, but if you take a stochastic algorithm, it is having advantage. I can say it can avoid a local optima trap, okay, and it will find a solution very quickly, okay, and it does not require any gradient. It does not require any grade. What's the problem with the stochastic algorithm? Is reliability. Okay, what is that problem? You see, I'm running the algorithm. Okay, it is giving one solution. I'm running the algorithm for the second time, it will give another solution. If I run the algorithm for a 10th time, it will give another solution. Okay, so that's the problem with the stochastic algorithm. Okay, but it will give the near optima, but not optima solution. Okay, so from this comparison, who is the winner? We can say the winner is based on the high local optima avoidance and gradient free mechanism. So whatever the algorithm is having the local optima trap avoidance and the gradient free mechanisms, yes, that algorithm will be the winner for most of the real world problems. So I can say based on the problems, okay, based on the problem nature, okay, just select which algorithm is required for you. Okay, so in my point of view, yes, the stochastic algorithms are more beneficial because it will find the solution quickly, it does not require any gradients, and it can avoid from the local optima. Okay, so this is my perception. It's not like it's always same. Okay, so now I'll just go to the another classification. So it's a individual based algorithm and population based algorithm. Maybe you hear about this word population based algorithm. So just see that this is what the problem. You can see that this is what the problem. Okay, and this is what we can say population. Okay, population or the search agents, or we can say the search agents or particles. We can say you can see only one person is there to find the solution in this multimodal problem. Okay, and but here you see that there are 5 persons are there, that is population number is 5, okay, or the search agents is 5, or the particle is 5. Okay, the 5 persons are trying to find the solution. So here only one person is trying to find the solution, but here the 5 persons are trying to find the solution. So in this you can easily say which algorithm is faster. Okay, which algorithm is having the lot of advantage. Yes, so this algorithm, if you take only one person is there, he itself the decision maker, right? He itself a decision maker. Okay, for example, if he is going, if he says that this is the local optima, if this is the global point, yes, because the decision maker is that person. So if yes, he will accept that this is the my global point. Okay, but actually to say it's not the right one, right? Because there is no decision maker here. But if you take this problem, this algorithms, you can see that 5 persons are there. The each person will tell, okay, this is what my global, this is what my global. So for each iteration, no, all the 5 population will try to find the best solution. It will be updated and it will be shorter for the, it will be shorter the ascending order. So based on that, finally all the population will move towards the global point. Okay, so from this I can say this is having more advantage, okay, and this is having a less advantage. Yes, but this will take more time because 5 populations are there. Okay, yes, they each one will give you a different solution, but here it can reach the point, it can reach the solution quickly, but yes, a lot of global local optima traps are there. Okay, yes, so you can see the individual base. So one simple example I will take. Okay, so this is a treasure. It is there in some mountain. Okay, and this treasure, if only one person is there, okay, you can see that this is the big treasure, and here you can see some kind of small coins are available. Okay, only one person called Jennifer is there. Okay, she wants to find the treasure. Okay, when she is finding where the treasure is, you can see that if suppose if she see this small one, if she see the small one, okay, she thought that okay, this is the best one. Okay, this is what the treasure we are looking for, so I am just take it, and she will run away. So it means you can see that she is trapped by the local optima. But here you see the Bob, Anthony, and Jennifer. So there are three persons. Okay, three persons are looking for the treasure. You can see this person is saying this is where the treasure is. This person is saying this is where the treasure is. But this person is saying, okay, here you can see the best treasure. Okay, so now based on the decision, okay, all the population will move towards the best treasure and they will take and they will run away. Okay, this is what a simple example for the individual based and population based algorithms. Okay, so what is the advantage and drawback? As I told you, local optima trap is more. Here, the local optima trap is very less. Okay, but the one advantage is with the individual based is it requires only very few function evaluation. Okay, but here if you see, it takes multiple evaluation. For example, if the problem is having 5 number of population and 1,000 iterations, so 5 into 1,000 is 5,000 function evaluation will happen. But if you see, I mean, the individual based algorithm, population is always 1, the number of iteration is 1,000, so the number of function evaluation is only 1,000. So obviously I can say the individual based algorithms will take a minimum function evaluation, the population based algorithm will take high number of function evaluation. So that's why the time will be more. Okay, convergence speed is somewhat lesser than this one. Okay, yes. So now the very important feature of any algorithm, okay, is called the exploration and exploitation. Okay, this is very important phases of the algorithm. Okay, so what is exploration and what is exploitation? So from the picture itself, you can easily differentiate what is exploration and exploitation. So the exploration means the search for the promising solution, and exploitation means preferring a good solution. You can see this is one, the telescope is given. So you see, when the problem is there, we'll be giving the search area, right? So when the algorithm is running, it should explore throughout the search area and it should find the solution throughout the search area. So this we call it as the exploration. Okay, then exploitation means, okay, it is finding the solution throughout the search area. If one population finds this is the best location, then all the population will move towards the best location and everything will converge to that best location. That we call it as the exploitation. Okay, so here you can see the microscope. Okay, this is a telescope, you can see the complete search space, and this is a microscope, you can see only the particular location. So that is what the difference between exploration and exploitation. So now you can easily design for the algorithm what should be the exploration and what should be the exploitation. Okay, so if you take any algorithm or if you design any algorithm, it should balance. Okay, it should have the balance exploration and exploitation. Okay, because if we have more exploration, you see, it finds the solution randomly throughout the iteration, finds the solution randomly. It cannot find the global point. If you have excessive exploitation, yes, what will happen? No, it will be trapped by the local optima, so that it will be converged very quickly in the local optima point. Okay, so the excessive exploration is having a random search and excessive exploitation is having premature convergence. Okay, so for the better algorithm, these two phases should be balanced so that, okay, the algorithm can find the solution throughout the search space and also it can able to find the global point very quickly. Okay, so this is the very important phases. So to improve these phases, only a lot of improved algorithms are coming. Okay, so maybe you people wonder why the people are improving the algorithm. So this is only to improve the exploration exploitation capability of the algorithm. Okay, and this is again our further classifications of the population based algorithm. So lot of classifications are there. So here very few classifications are given. One is evolutionary, physics based, swarm based. Okay, then mathematics inspired. Okay, so many things are there. Then physics inspired, then human inspired. So many algorithm classifications are available. Okay, here I just listed very few algorithms. Okay, so in our today's discussion, we are going to talk about the swarm-based algorithm. One is a particle swarm optimization, and another one is the Gray-Wolf optimization. Okay. Yes. So now you may ask a question. So why the people are proposing new algorithms daily, or why the people are proposing the improved versions of the existing algorithm? So that is because of this theory. Okay, the no-failures theory. Okay, so what this theory says is, there is no optimization algorithm to solve all the optimization problems. Okay, so for example, I take one optimization algorithm. Even I'll take a particle swarm optimization algorithm. Okay, assume that the particle swarm optimization algorithm is giving a better result for optimal power flow. Okay, the same PSO, if you apply to some other problem, for example, maybe PID controller tuning, if you apply there, it doesn't mean that the PID is a PSO algorithm will give better result for the PID controller tuning also. Okay, so it may give the poor result for steady controller tuning. It may give good result for optimal power flow problem. So that's what this theorem says. There is no optimization algorithm, okay, to solve all the types of optimization problems. So based on this theory only, the people are proposing new algorithms and improved versions of the existing algorithms. Okay, so now yes, I'll move on to the first the algorithm for today's discussion, a particle swarm optimization algorithm. Okay, so first, who have invented this algorithm is Dr. J. Kennedy and the Dr. R. Eberhard. Okay, so the people are talking about, like, every day the people are telling that the algorithms can be developed by only the computer science students, right? It's not like that. See, this particle swarm optimization algorithm was designed by an electrical engineer. Okay, so Dr. R. Eberhard is there. So he is an electrical engineering professor. Okay, so they with this Kennedy is a psychology professor. You just see psychology professor and electrical engineering professor, both they have invented this algorithm. So you may ask why I have taken this algorithm for the discussion. So as I told you already, this is one of the very famous algorithm, okay, very famous and preferred algorithm throughout the world, okay, and it has citations so far about 75,800 citations so far till today. Okay, so that much famous algorithm it is. So that's the reason I have taken the particles form of optimization for today's discussion. Okay, even today, a lot of variants of PSO algorithms are existing. Even till today, the people are working on the PSO algorithm. Okay, so this is where the first algorithm published in the conference. Okay, in 1995, it was published. Okay, as I told, it reached about 75,000 citations so far. Okay, so what inspired to develop this algorithm? Okay, so the main inspiration is because of the swarming behavior of the birds flocking or the fish schooling. So this is what the motivation behind why they have created the particle swarm optimization. You can see that this is what the birds flocking and this is what the fish schooling. Okay, so based on this, you can see that the more than the lakhs of birds are flying to migrate from one place to other place, right? So here you can see a lot of birds are flying, but you can see that the path is towards the best location. So because one particular, the one bird is guiding everything, because that bird find that is what my actual target. So that bird is flying. So by following that bird, all other birds are flying. Okay, the same way the fish schooling are. Okay, so this is what the inspiration for the particle swarm optimization. Okay, now we will be discussing how to formulate this particle swarm optimization algorithm. Okay, and I'll just take one simple example to understand the particle swarm optimization algorithm. Based on that understanding, we'll be developing the particle swarm optimization algorithm. Simple one. Okay, yes. So now for to understand the particle swarm optimization algorithm, the whatever I told the previous stage, the same problem I'll be taking for understanding the PSO. So here you can see that one big mountain is there. Okay, so you can see a lot of hills are there. Okay, yes, you can see that the treasure I kept. Okay, and here, as you know, the PSO is a population-based algorithm. So there are three population. One is a Bob, Anthony, and Jennifer. Okay, and these three are the particles, or I can say the populations, or I can say search agents to find the treasure. Okay, and this is what my objective. I need to find the treasure, and these are all, I can say the population. And here you can see that rainy or thunder, everything is there, or maybe hot. Okay, these are all the constraints. Okay, so now here I just want to find the analogy. Now what we are doing is we are giving a GPS to the three people. Okay, and with the help of the GPS coordinates, the search agents or these people are going to find the treasure. Okay, and here you can find the analogy. Okay, analogy is nothing but the search space first. The search space is nothing but this entire mountain in the search space. So I can say this kind, we call it as a landscape or the search space. Okay, and the variables, as you know, the decision variables are required because with the help of GPS only, they are going to find the location of the treasure. So I can say the XY coordinates are the variables. Okay, and here you can see the Z is nothing but my objective value, or you can say the fitness value. Okay, and the GPS, because with the help of GPS only, because I need to find the treasure with less distance. So obviously I can say my GPS is the objective function, and all the possible locations or the throughout the search space they have to find. Okay, and as I told, the constraints are the rain, flood, or whatever it is. Okay, and the treasure is nothing but your global optima. Okay, and the small coins are nothing but the local optima. Okay, and here the search agents or the populations are Bob, Anthony, and Jennifer, and the algorithm is nothing but your search strategy. Okay, and number of days, because they'll be finding the treasure, it is not in a day, right? So they will take multiple days because they don't know where it is, right? So they'll take a number of days to find the treasure. That is nothing but your iterations. Okay, and the target is nothing but your optimization. Okay, this is what a simple analogy. So with this simple analogy, okay, I'll just explain. Okay, so what are the things that people have to do? Okay, so as I told you, there are three populations are there. So here one condition is each person has to walk. Okay, each person has to walk 10 kilometers towards the personal best, and 10 kilometer towards the team best, and 10 kilometer towards the current direction. So each person has to follow this rule. Okay, so for example, the Bob will move towards the personal best location for 10 kilometer, and he will move 10 kilometers towards the team best. Team best means the Anthony and Jennifer. Okay, team best location, and the current, in the current direction, whatever the direction he is walking, in the current direction he has to walk for 10 kilometers. Okay, if I represent in vector, maybe you can understand in better way. You can see this is what the Bob. Okay, and this is a current direction. Okay, and this is the personal best direction, and this is the team best direction. Okay, as I told you, in each direction he has to walk for 10 kilometers. Okay, the first he has to move towards the current direction for 10 kilometers. You can see that. Yeah, you can see that. You see the Bob is moving towards the current direction for 10 kilometers. Okay, then from there he will move towards the personal best location for 10 kilometers. Okay, and again from that point he'll move towards the team best location for 10 kilometers. Okay, finally he will be moving from this place to this place. Okay, this is what we call it as a position update. Okay, this we call it as a position update. So from here to here he'll be going. Okay, now again he has to follow the same rule. Okay, from this point again he has to move towards the current direction and personal direction and team direction. Okay, then finally he'll be moving to the next place. Okay, you can see in each way he is moving. You can see that in the current direction he is moving 10 kilometers. Yes, he is moving towards the personal base and the global base, and finally he'll be moving this place. Okay, so finally you can see that. Okay, yes, I'll just show you the final one. See, initially he was here. Okay, and after a certain time, okay, he moved here, and after a certain time he moved here. Okay, maybe here you can say day one he reached here. Okay, and day two he reached here. It is nothing but iterations. Okay, during the first iteration he reached here, and during second iteration he reached here. Okay, and maybe third iteration he'll be moving here, and the fourth iteration maybe he'll be moving here, and fifth iteration maybe he'll be moving here. He'll be moving here, and sixth iteration maybe you can see that. Finally you can see in the previous one, the previous slide, you can see that initially he was here. After fifth day he was here. But you see in this iteration he couldn't be able to find the treasure. Right, so that's what the problem. Suppose if the Jennifer is there, she also moves in the same route whatever we have given. Okay, maybe she can find. or the Anthony is there, he also move based on the rules what we have formulated, and he may find the treasure, right? So that's what here you can see. Suppose instead of 10 kilometers, if I ask the person to move 20 kilometers, just see here. So he is moving towards 20 here, 20 here, and 20 here. So finally, after first iteration, he moved here, right? So to mimic this in mathematical term, what I have taken now, 2 times of the distance what I have taken, okay, into the random variable, because he don't know where to move, right? Or randomly he will be moving it. So here we are introducing one random parameter. So where this or is nothing but uniform random number, it will be vary between 0 to 1. Okay. So now you can observe, day 1. Yes, he'll be here. And that means day 1, he can cover this much place. Okay. And in day 2, he can cover this much place. And day 3, he can cover this much. Day 4, he can cover this much. Day 5, he can cover this much. But still, he couldn't be able to find the where the treasure is. Right. So initially, we started with 10 kilometer. Now we started with 20 kilometer. But still, he couldn't be able to find the distance, or he couldn't be able to find the location of the treasure. Right. So now if we consider all 3 people, okay, the Bob, Anthony, and Jennifer, all 3 are finding, everyone is following the same rule, but you just look at it, this Jennifer can able to locate the treasure in some iteration. So once she find, now what will happen? That information will be shared to the Bob and Anthony as all these people will move towards the treasure. Okay, so this is what a simple understanding, of the PSO strategy. Okay, so what we have to do is first, each population will try to find the solution randomly, and they will keep update the position of the location throughout the iteration, and finally they could able to find the global value. So this is what a simple analogy of the PSO. Now, with the help of this basic understanding, okay, you see, I have to formulate the velocity equation. So in PSO algorithm, only 2 equations are required to formulate an algorithm. Okay, so the very first one is the velocity, because each person is moving with certain velocity, correct? So I have to find the velocity. So the velocity during the next iteration. So the VI is nothing but, this is I represents your population. I is equal to 1 to n. N is nothing but number of populations. Okay. And here D is nothing but your dimension. Or sorry, your D is nothing but iteration. Okay. So D plus 1, it is nothing but for the next iteration, what will be the velocity? Okay. So that I need to formulate an equation. So that is equal to the current velocity. What is the current velocity? At present, what is this velocity? That is VI into D. As per our discussion, I told you, right, 2 times of my speed I'll be going. So in my previous discussion, I told my VI is the velocity is equal to 10 kilometer I have taken, right? Now we have taken 20 kilometers. So for that, I just multiply with 2. So 2 into R1. R1 is nothing but your random number. So my velocity at next iteration is equal to 2 times of my current velocity into the random number, because he has to find the solution randomly, stochastically. He has to find the solution plus. Okay, so as I told, each person has to move towards the current direction, personal best direction, and the global best direction, right? So to mimic that one, to mimic the personal best direction, you can see that they will be finding the distance between the actual position and the personal best position. See that this is the personal best position, okay, minus this is what the actual position, and that again multiplied with 2 times of my random number. Okay, this again R2 is nothing but a random number. Okay, and plus you can see 2 times of R3 into the global best, because as you know that each person has to move towards the current direction, towards the personal best, and towards the global best also, right? So the global best distance also we have to find. So this is the global best distance. Okay, that is the global best position minus the actual position, and that will be multiplied with 2 times of my random number or 3. Okay, so here 2 is nothing but your constants. Okay, 2 is nothing but your constants, and R1, R2, R3 is nothing but your random numbers, uniform random number. It will be varied between 0 to 1. Okay, so Now I'll just simplify the equation. Okay, I'll just simplify the equation. You can see that my final equation, how it will be. Okay, so once I find the velocity, you see in this slide, we discussed how the velocity is found. Once the velocity is known, I can update the position, right? That's what we saw in the picture. He'll move 10 kilometers in the current direction, 10 kilometers towards the personal best, and 10 kilometers towards the global best. So complete thing is nothing but the velocity. So now initially he was one position, then after that he'll be moving to the other position, right? So to mimic that one, okay, to mimic that one, here you can see this is what the position update equation. The position update is equal to the current position plus the velocity at the next iteration. So based on that, he will be moving towards that point and he will be halting there. That is during day one. Then he'll go for the next iteration. He'll move toward the next place, and he'll go to the next iteration, and he'll move towards the next place. So it means for each iteration, he or she can have to update its position. So now based on the complete discussion, you see that this is what the two equations required to formulate the PSO algorithm. One is the position update equation, another one is the velocity update equation. You can see all the numbers 2 or 1, 2 or 2, 2 or 3 we have used, right? Everything is replaced with the constant. So here you can see that the velocity constant W is nothing but inertia constant. Okay, so this is a constant number, or it may be anything. Okay, that while formulating the PSO algorithm, I'll tell you what is the impact of this W. Okay, and the C1, again, it is a cognitive component. Okay, it's a cognitive coefficient, and C2 is again a social coefficient. Okay, so these again C1, C2 is also a constant number. It may be adaptive number. So based on the requirement, we can change it as a constant, or we can change it as a adaptive numbers. But this R1, R2 is completely a random number. So first we'll be calculating the velocity. After calculating the velocity, we'll substitute here. We'll be finding the next position update of the particle. Okay, so only these two equations are required to formulate the PSO algorithm. Okay, so now we have to understand here, you see, for the PSO algorithm, there are 3 parameters are required. So we can call these parameters are algorithmic parameters. What are the 3 parameters are? W, C1 and C2. These 3 are the parameters required to fine tune to apply to any of the real world problems. So what is the impact of these 3 parameters? Okay, so that you have to understand here. You can see that, you see here, so I think it's not, yeah, okay. You can see that iteration you can observe here, and I kept the W is equal to 0.8, and the C1 I have taken as 2, and C2 I have taken as 2. Okay, so now at the first iteration, the populations are randomly distributed. Okay, once the iterations are progressing, see here you can see the number of dots are there, right? Number of dots are nothing but your population size, or number of particles, or the number of search agents. Okay, so when the iteration started, it will be randomly distributed throughout the search space. So this is nothing but a search space. This is nothing but a search space. Throughout the search space, it will be randomly distributed. And once the iteration progresses, everyone will move towards the global best. You can see that one person find the best solution. Now you see that all the populations are moving towards the best solution throughout the iteration. Okay, this is for W is equal to 0.8 and C1 equal to 2 and C2 equal to 2. You see that even it would, after 100 iteration, even after 100 iteration, it couldn't be able to find the proper, because all the populations are not converged to the best solution. Can you observe it? Yes. So now what I'll do now, I'll change the parameter W. I'll change the parameter W to 0.1. You can see the same C1 equal to 1, C2 equal to 1 I have taken, and W is equal to 0.1 is taken. And now in this diagram, you can see my W is equal to 0.8 and C1 equal to 1, C2 equal to 1. And here the W is taken as 1. You can see that C1 equal to 1 and C2 equal to 1. So now when you observe this animation, you can be able to understand the first figure. You can see the first figure, it will converge very quickly. It will converge very quickly. But you see the second figure, it also converges to the possible solution. Okay, that is the best solution, but it takes some more time than the first one. Okay, but when you look at the third figure, you see that throughout iteration, it couldn't be able to reach the global solution. Okay, so this is what we can easily classify the exploration and the exploitation. So now if I take this figure, the figure is having more exploration. Because you see, even after 100 iteration, couldn't able to find the solution because it is finding the solution through the search space. So it explores more. So the exploration is more, exploitation is less. Okay, and here you can see that exploitation is less, but exploitation is more and exploration is less. Okay, so that's why here it could able to find the solution very quickly, but sometimes, okay, sometimes it will be trapped. Okay, but if we check this, you see, it has more exploration and it has more exploitation also. It means both are balanced so that it could able to find the best solution. Okay, this is what the impact of your cognitive and social coefficients of the PSO algorithm. Okay, still, so here you see, you observe the convergence for the different values of W. Okay, now what I'll do now, I'll take the next example. I'll fix the value W. Okay, and I'll change the value of C1, C2 values. Okay, in the first figure, for all the three case study, I have taken the weight, that is the inertia weight is 0.1. Okay, but for the first figure, the C1, C2 value is 4 and 0. And for the second figure, C1, C2 value is 2, 2. And for third figure, the C1 value is 0 and C2 value is 4. Okay, so now if you observe the figure, you just observe the figure, I have taken C1 equal to 4 and C2 equal to 0. So if I take C2 equal to 0, it means that we are completely omitting the decision of the global best. You are talking about only the personal best. So when you're talking about the personal best, you see that each person is thinking that my solution is better. That's why, so none of the population could able to find the global solution. So you see, through the equations are running, but everyone is stagnated, right? It's because of more highly explored. Okay, because everyone is saying that my location is best, everyone is stagnated there. So, but when you look at this, C1 equal to 0 and C2 equal to 4, it means you're completely omitting the personal best. Okay, because your C1 is 0, you're completely omitting the personal best. Okay, and you're taking only the global best. So when I take the global best alone, you're omitting the personal best, and when you're taking the global best alone, it cannot able to find the optimal solution very quickly. It will take much time. Okay, but you see, if both are balanced, you can see that it would able to find the solution very quickly. So I can say here more exploration is there, and here we have more exploitation, and here you can see that both are balanced. Okay, so from these two discussions, what I can say is the exploration and exploitation of PSO is controlled by C1, C2, and the inertia constant W. So if you want to use this algorithm properly for your application, you have to fine tune the value of W, C1, and C2 for your problem. Okay, so then only you can find the best solution, or else no, yes, you will not get the best solution for your problem. Okay, so I think you understand what is PSO algorithm, what are the equations are required to formulate PSO algorithm, right? And what are the impacts of the coefficients like C1, C2, and the weight factor called the inertia weight, that is W, right? So we have to select the proper one. And one more thing here you can observe. So whatever we saw here, it is having only one global optima. Here, just see, it is a multimodal problem. It is a multimodal problem. So in all the previous slides, what we observed is we kept W constant, C1 constant, and C2 constant, right? Suppose if I make these constants adaptive, so it means throughout the iteration, if these values are changing, okay, what will be the impact of the algorithm? So that you can observe here. Just observe this, okay? See, throughout the iteration, my W values vary, and C1 and C2 values also vary. You can observe it. So when we have the adaptive parameter, my solution will get the solution very quickly. There is a chance of getting the solutions very quickly. It means you're improving the exploration and exploitation capability of the PSO algorithm. Okay, that you can easily observe it. My W is also changing, and C1, C2 is also changing, so that it quickly converts to the global optima point. Okay, this is another solution. This is another solution. Here also you can observe that W value is taken and C1, C2 value is also changing throughout the duration. And here you can see that is my solution is quickly converged, Okay, so this is what the impact of C1, C2, W. So when you use PSO algorithm for your problem, please take care. Please take care. You have to fine tune the W. So how to find the values of this? So the only method is what we have the trial and error method. Okay, just by trial and error method, you have to find the values of W, C1, and C2. But nowadays, what the people are doing, because of the lot of advancements are happening in the machine learning. Okay, they use some kind of machine learning algorithms to fine tune the hyperparameters of the parameters of these kind of algorithms. So we have certain algorithms are available to fine tune these parameters. That is also available. Okay, so that is the out of scope of this discussion. Okay, if you are still interested, you just try to refer some papers, the hyperparameter tuning of the algorithms, meta-heuristic algorithms. So you can find so many papers. We have so many methods to fine-tune the parameters of the meta-heuristic algorithms. Okay, or else if you don't have the awareness about that, what you have to do is just by trial and error method, you have to find what is the value of W, C, and C2 is the perfect for your problem that you have to find. There is no other way. Okay, so now the pseudocode of the PSO algorithm. So you understand the pseudocode. Now, with the help of the pseudocode, we'll be going to write the PSO algorithm now. Okay. So first and foremost thing for all the meta-heuristic algorithm is you have to formulate, you have to initialize the control parameters of any algorithm. So here we are talking about PSO algorithm. The first thing what you have to do is you have to initialize the controlling parameters of PSO, that is N. N is nothing but population size, and C1, C2 is nothing but your coefficient, social and cognitive coefficient. Okay, and W min and W max is nothing but a minimum weight and maximum weight, because I'm going to adopt nonlinear equation to change the W value. Okay, and V max is nothing but maximum velocity of the particle. Okay, and the maximum number of iterations. These are all the parameters need to be initialized first. Okay, once all these parameters are initialized, what you have to do is you have to generate a random population solution. Okay, you have to generate the random population solution. After finding the random population solution, what we have to do is we have to sort it out. Okay, so this is the very first step you have to do in the PSO. Then next, what you have to do is we'll go to the main loop. Main loop means what? Here the termination criteria. So the termination criteria here is the maximum number of iterations. So now here I'll keep while loop. Okay, so if my while loop, if the while loop is if the iteration is less than or equal to maximum number of iteration, it will compute all these steps. Okay, if it reaches the maximum iteration, it will come out of the loop and it will return the best value. Okay, so in each iteration, what will happen inside the loop? Okay, what we have to do is for each particle or for each population, first what we have to do is you have to find, or you have to calculate, or you have to compute the objective value of the particle, because already we have assigned the particle randomly. Okay, so for these random particles, first you have to find the objective value. After finding the objective value, I'll be comparing this objective value with the personal best value and the global best value. Okay, so based on that, I'll be updating my personal best and the global best location. Okay, so this is this will happen for each particle. The next one is update the inertia weight. So as I told, the inertia weight you can take as a direct constant number. So here for my discussion, what I'll be taking now, I'll be taking my inertia weight is some kind of adaptive equation or some nonlinear equation I have taken. So it means for each iteration, my W value is going to change as like what I have shown in the previous slides. Okay, so now after updating the inertia weight, for each article, because we told no two equations, one is a velocity equation and one is the position equation, right? Position update. So with the help of velocity equation, I'll update the velocity. Okay, with the help of position equation, I'll update the position. Okay, after that, this will be continued. This will be continued throughout your iteration. Once the maximum iteration is reached, yes, it will return the global best value. Okay, you please understand the pseudocode of PSO. Then once you understand the pseudocode, yes, we can easily write the algorithm. I'm not going to copy paste the PSO algorithm from somewhere. Okay, it's like a hands-on, as I told you. Okay, along with you people, I'm also going to design the PSO algorithm now. Okay. So now, as I told, after formulating the PSO algorithm, okay, we'll be solving one simple example. Okay, so here what example I have taken is one simple function, that is a sum of x square. I'm going to find. This is my objective function. F of x is equal to sum of x square. I'm going to find. So here the x is nothing but the decision variable or the decision vector or the problem dimension. They technically they'll call it as a problem dimension. Okay, for my discussion, the dimension is taken as 2. That is sum of x1 square, that is x1 square plus x2 square. That is what my equation is. Since I have taken the dimension is equal to 2, f of x is equal to x1 square plus x2 square. So I have to minimize this function. Okay, I have to minimize this function value. So for this, I'll be taking the maximum number of iterations equal to 500 and maximum number of particles or the populations I'll be taking it as 30. Okay, as I told you already, we have a decision variable. For each decision variable, we have to define bounds or the limits, right? So for this variable, as I told, I have taken 2 variables. For 2 variables, I have listed my the lower limit and the upper limit. So the lower limit for both the variable is -100 and -100, and the upper limit is +100 and +100. So now you can see this problem is very simple, right? Yes, you can easily tell what will be the solution of x and x1 and x2, right? It should be equal to 0, 0, right? Then only you can see the objective function value 0. So I can say the minimum f minimum value for this particular objective is 0. So your algorithm has to find 0, okay, just by optimizing the value of x1 and x2. So that is what the simple example I'll be taking for today's discussion. Okay, so we'll increase the dimension. When we increase the problem dimension, what are the problems with algorithms? So that also we'll observe today. Okay, this is an example I'll be taking for today's discussion. We'll have a lot of examples, so that also we'll discuss if time permits. Okay, then the second one, the very important one, is the parameter estimation of the photovoltaic cell. Okay, this is a real world problem. Okay, and here you can observe that for the parameter estimation of the solar photovoltaic models, as everyone knows, we have single diode model, double diode model, and 3 diode model. So many modelings are available, mathematical models are available. Okay, so for today's discussion, possibly I'll be taking both the single diode model and the double diode model, and I'll be telling you how to solve this problem with the help of PSO algorithm. Okay, then we'll move on to the variable algorithm. Okay, this is a single diode model. As everyone knows, the single diode model is having one diode which is connected with controlled current. The controlled current is that is controlled by irradiation. We have a current source here. You can see the current source is there. Okay, and we have a diode. Okay, we have a diode, and here you can see that some ohmic resistances are there. Okay, just to mimic the leakage current of the panel and the terminal resistance of the panel or the cell. Okay, so we have a series resistance, we have a shunt resistance. Since we have a diode, okay, the parameters related to the diodes are, the diode ideality factor and the diode reverse saturation current. So these two are the parameters of the diode. And here another parameter is called the photocurrent. Okay, the photocurrent. So now I'll be writing my equation, the PV current equation. From this simple equivalent circuit, I'll be writing the PV equation. My total current through the cell is equal to the photocurrent minus the diode saturation, diode current minus shunt current. Actually, this direction is somewhat reverse, so sorry for the mistake. So the direction should be in this way, towards upward. Okay, so I just sorry for the mistake. Okay, so the total current is equal to the phase current, that is photocurrent, minus, because entering current is equal to leaving current, so that is your I phase minus ID minus ISH. So I have taken this total current equation. So now, as per by applying Shockley's equation, I can write the diode equation. So if I write the diode equation, you can see that IPV is equal to I phase minus by applying Shockley's expression, I'll be defining the equation for the diode, that is ISD into exponential Q into VPV plus IPV into RSC divided by AKT minus 1. This is by applying Shockley's equation. We have written the diode equation. And here you can observe that ISD is nothing but diode saturation current, and Q is nothing but electron charge. Okay, VPV is the output voltage of the cell. IPV is nothing but output current of the cell. Okay, RSC is nothing but series resistance of the cell. Okay, and A is nothing but diode ideality factor. Okay, and the K is nothing but a Boltzmann constant, and T is nothing but cell temperature. Okay, so now my minus ISH is nothing but shunt current flows through this. So this is equal to V plus IPV into RSC divided by RSH. So that is also written here. So this is what the output current equation of the PV cell. This equation is required to model the objective function. Okay, so keep this point in your mind. This is the very important equation, the mathematical equation to formulate the objective function. Okay, similarly, we have the double diode model. Okay, double diode model, you can see that there are two diodes. Okay, so if you want to find the output current of the cell, you can see the same equation, I phase minus, there are two diodes. So you have to apply Shockley's expression for both the diodes. You can see here, this equation is for the diode 1 and this equation is for the diode 2. Okay, and finally, my shunt current. Okay, you see that here ISD1 is there, that is a leakage current of the first diode, and A1 is there, the diode ideality factor of the second diode. And here also you can see the leakage current of the second diode and ideality factor of the second diode. Okay, and here you can see RSH is there. So this is applicable for the cell. Suppose if it is a module, yes, as you know that how the modules are formulated, the number of cells connected in series parallel way, so that we can make a PV panel or a PV module, right? So here you can see that NSC and NP is nothing but NSC is number of cells connected in series and NP is nothing but number of cells connected in parallel. Okay, but for today's discussion, I'll be talking about only the cell model, not the panel model. Okay, so now just look at this equation and look at this equation. Only these two equations are required. Now, if I look at this equation, I can say only 5 unknown parameters are there. You can see what are the unknown parameters. My photocurrent is unknown. The saturation current is unknown. Okay, and the ideality factors are unknown, but these values are known, right? So the temperature, everything is known. And here you can see RSC is unknown or RSH is unknown. So for single diode model, the unknown parameters or the parameters to be optimized is 5. One is IPH, ISD, RSC, RSH, and A. These are the 5 parameters need to be computed for single diode model. Similarly, for double diode model, there are 7 parameters. You can observe it. You see, I phase is there, ISD1 is there, A1 is there, ISD2 is there, A2 is there, and RSC and RSC. So I can say there are 7 parameters to be optimized or to be calculated for the double diode model. Okay, so we have 2 equations and we know what are the unknown parameters. So from this, I can say the problem dimension for the single diode model is 5. 5 unknown. So 5 is the problem dimension. And here you can see there are 7 unknown parameters. So I can say my problem dimension is 7. Okay. Yes. Now we have to formulate what? Objective function, right? So for most of this problem, we will be taking the RMSE as an objective function. RMSE is nothing but root mean square error. Okay. So this will be calculated. This will be formulated first. Then this will be solved with the help of the optimization algorithm, and we'll be finding the unknown parameters. So here you see, this is what the root mean square value. You can see the square root of 1 by x. X is nothing but number of data samples. Okay, number of data samples. I'll tell you when we solve the problem. Okay, when I formulate the equation, I'll tell you. Okay, and for each sample, you have to minimize the function. Okay, what should be the function? The function is nothing but, you see, f of v comma I comma y is nothing but I phase minus id exponential component minus v plus I divided by rp minus I. So this is what your actual current. Okay, this is what you can say my estimated current, and this small this I is nothing but your current taken from the data sample. Okay, so from this, you can easily observe, I'm going to find the error between the estimated current and the actual current. Okay, and here I can say my unknowns are totally 5 unknowns. So I can say these are all my uh, problem dimension. So similarly for this two double diode model, okay, you can see the same equation is written. I faced the whatever we have written here, the same is written here. See, this is what I can say my estimated, I'm going to estimate the current by optimizing the values, and this is nothing but my actual current taken from the data sample. I'll be finding the error between the estimated current and the actual current. So here the decision vectors or the problem dimensions are 7. So these are all the problem dimensions. Okay, so you may ask the question, sir, okay, the objective function is formulated, why we need optimization algorithm? As you know, this equation, when you look at this equation, this is completely a nonlinear and transcendental equations. Okay, to solve this equations, obviously we need some kind of analytical methods or the numerical methods or some kind of heuristic methods. We can go with any methods. Maybe you can use some kind of interruption method to solve, or maybe you can use some kind of Levenberg-Marquardt method, okay, or you can use heuristic algorithms, any kind of heuristic algorithms, you can use it to solve this highly nonlinear equations. Okay, so with this, my theoretical discussions are over. Okay, now it is the time to develop a PSO algorithm, and we'll be testing the same with the numerical problem and parameter estimation problems. So I hope you people are ready. Yes. Are you people ready? Can we start the hands-on session? Are you people ready? Are you people listening? Yes. Okay. I could see some questions.
Doctor, you will say any questions or directly we'll go to the program formulations?
Yes, I think someone has asked, is this a single objective? Yes, it's a completely single objective problem. It's a completely single objective problem. So now when we solve, no, when we have hands-on, yes, you can easily understand what is the problem nature. So I hope everyone is having the MATLAB. You please open the MATLAB and open a new M5. Okay, just open a new M5. Okay, so I just save this file as a PS4 draft and just keeping it PS1 draft. Okay, so first for each execution, I need to clear all my files. Okay, so I just keep CLC. So for each iteration of for each run, I'll be opening, I'll be making one figure. So I just want to close the figures for each execution. So I just keep this CLC clear all and close all. I just keep it. Okay. So now let me start. Let me start the algorithm part. So as everyone knows, so what is the first part of the formulation? You see, we have to initialize the control parameters, right? We have to initialize the control parameters, nothing but n equal to C1, C2, n C1, C2, W min, W max, V max, maximum iterations. Okay. Now for simple discussion, I'll be omitting the V max. I'll be telling you the impact of V max when we solve the problem with PV. Okay. Yes. So first I'll be writing my number of population. So I think we take any variable. I'll take my n is equal to some 30. As per our discussion, I'll be taking 30. This number of particles. Okay. So I can say it is number of particles. Yes. So next we have to define the maximum number of iteration. So I will be taking my maximum number of iteration is equal to some 5. Whatever you want, you can take it, not a problem. Okay. Yes. This is the second parameter. And third parameter, as you know, the C1, the cognitive coefficient. So I'll be taking as a constant. So I'll be taking C1 equal to 2. And C2 is also taken, social component. So that also I'll be taking it as 2. Okay, as I told you already, the W will be the adaptive one. Okay, first what we will do now, we'll take W as a constant, then we'll go for the next one. Okay, I'll take W is equal to 0.1. I'll be taking the W as constant now, just for formulating the simple P as well. Okay, so this is done. So N is done, maximum iteration is done, C1, C2, W is done. Right, so now what we have to do. After initializing the parameter, you just look at the presentation, you can see initialize the population of n particles that we have to do. Okay, so how to do this? So as you know, in the PSO, we have the personal best and the global best is there, and the current position and the velocity is there. So all these need to be initialized first. So first I'll be taking personal best. P best is equal to P best fitness. Okay, P best is equal to, I'll be taking for the start of the algorithm, I'll be taking all the values of 0. Okay, I'll be taking all the values of 0. Okay, you can see I just run it. You can see the P best. Okay, just P best. All the values for 30 cross 30 matrix it will create. So all the values I'll be taking it as 0 now. Okay, now P best position. I'll take P best position. Okay, position of the personal best. So this is the fitness of the personal best. Okay, this is the position of the personal best. So this will again, this also I'll be taking it as zeros of. Okay, since we are finding the position, we have to consider n comma the dimension. So see, we forgot to find like the dimensions. So the dimensions for the problem what we have taken is dimensions equal to 2. Yes, and we'll be writing the lower bounds and upper bounds. So LB and UB values also will write it. Okay, so I'll take -100 and -100, two variables. So I have taken is like this, and UB is equal to yes +100 and +100. I have taken it. Okay, so now you see that how the personal best positions are now. I just run it. You can see how the personal best positions are. You can see since it is a two variable, you can see that 30 population. So you can see for all the three variables, we have for all two variables, we have assigned 0 initially. Okay, so this is everything you have to do. This is common for all the algorithms. Okay, it's not only the PSO. Okay, so once the P best is done, the next one is what we have to do is we have to find the G best value. Okay, so G best solution. So that is also I'll be taking zeros of 1 comma dimension. Since it is a G best, since it is a G best, it should be like 1 comma dimension. That is G best position. Okay, so again I run it. You can see the G best solution. I'll be taking, because G best means global best means only one always, right? So we cannot find different population, different values will be there, out of which what is the global value that will be displayed the G best value. Okay, this is also done. The next thing is, yes, I'll be writing my position. Okay, I'll be writing my position. That is my current position. Okay, so current position again, I'll be for everything, I'll just take it initially as 0. Okay, then I'll start it. Okay, so my position is also, yes, I have taken, and my velocity is also I have taken as 0. So velocity is also taken as 0. Everything I have taken initially 0. Okay, yes. Now after this, I just initialized all the matrices, everything I just initialized it. Okay, then I told you one thing. What I told you is we have to generate the random population position. For each random population position, we have to find the fitness. So this is what the statement I told you, right? Now I have to create a random population. Okay, how to create the random population? So I'll just take one for loop. Okay, so for loop I is equal to 1 to n. Okay, just in this. Yes, inside I'll take another for loop, because for each population and for each problem dimension, we have to find the random solution. So for j is equal to 1 to dimension, I'll be taking another thing. Yes. Okay. Yes. So now what we have to do, we have to generate the random position, right? So my position already we have defined it. Okay, position of I comma j, position of I comma j, because for each population, for each dimension, I have to find I have to generate random solution. So it is equal to, yes, ub, because that random position will be generated within the defined search space, within the defined search space. So that what I'll be doing is I'll be taking ub of j J is the dimension, right? So UB of J minus LB of J into random, because we have to generate randomly. So it is, I have taken my simple random number, okay, plus LB of J. Okay, you see that my position, see, initially I assigned my position as 0. Okay, now what I did is I just generated random population position. So I just run this. Now you observe, okay, zeros. Sorry. I just run this. Okay, now you just look at the position of the things. You see, within the define the search space, randomly the values are assigned. Here you can observe it. Randomly the values are assigned. See, now this is one value. Okay, if I run once again, this values will not be same like previous one. So because this random number for each execution, this random number will changes, so that for each execution, the position will be changed. Okay, so the same way we have to assign the velocity also. Okay, so velocity is simply I'll take the random velocity. Okay, so as I told, we have taken 2 times of random now, so I have to be taking 2 times of random. Okay, now you can see the velocity also, velocity matrix also. You see, velocity matrix also generated. So I hope you are clear up to this, right? Any doubts? If not, I'll just move forward. Okay. Yes. So now what we did so far is for each population and for each dimension, we just created the random velocity and random position. It's done. Okay. Now what we have to do is we have to find the P best. I'll be defining my P best of 5. That is for each population. For each population, my personal best will be equal to infinite. I'll be taking. So why I'm telling this now? This is very important one. This is very important one. Why I'm telling this? Yes. So someone is asking what is the difference between P best and P best position. See, P best means it is the fitness. P best position means the position of that particular fitness. See, for example, we have a lot of party. The Bob is there. Okay, so Bob can get the information from the personal best and also the global best, right? So the Bob position is there, right? Bob position is nothing but P best position, and for that particular position, we'll be having the fitness value, right? So that is nothing but P best. Okay, I hope you understand. P best position is nothing but the location. P best is nothing but the particular location fitness. Okay, so this is required, very much important. Okay, so here you just see, I have already I defined P best, and here again I'm defining my P best is infinite. Initially I'm taking the P best is infinite. Why this infinite word I kept? No, because as I told you, the problem may be the minimization problem or the maximization problem, right? So if it is the minimization problem, initially you have to start all the solution with infinite. If it is a maximization problem, you have to start the solution with minus infinite, so that the problem will be converted to the maximization problem. Okay, that's why I'm telling you this is very important step, so don't forget it. Okay, so initially my P best I just assigned as 0. Now for each population, I'll be telling my fitness value, my personal best fitness is infinite, so that I'm just configuring my algorithm to the minimization problem. So I'll just run this. You just look at your P best. You see the first solution is always, it's infinite, completely it is infinite. Okay, so just to define my problem is, minimization problem. So similarly, G best also we have to say, right? G best is also equal to infinite, because it is a simple minimization problem. So this is what the second step. You see, initialize the population of n particles. So we did everything now. So what we did, we just defined all the algorithmic parameters, and the bounds and the dimensions are given. Now, to formulate the PSO algorithm, as you know that you should know the current velocity, current position, personal best position, personal best solution, that is the personal best fitness, and global best solution and global best fitness. So everything is done. Okay, So now what I'll do now, I'll just open the while loop. Okay, I'll just open the while loop now. Sorry, a while loop, any loop you can use it. Okay, any loop you can use it. So because we have to run this algorithm up to the termination criteria. As I told you, the termination criteria is the maximum number of iteration. So what I'll do now, I'll take a for loop or while loop, whatever you take it. Okay, so I'll take a for loop. So for loop, I have taken t is equal to 1 to maximum iteration. So maximum iteration. So this is what we already defined it. So we'll just end it. So this is what your main loop. Okay, this is your main loop. Okay, so now initially I start with 0. I start with 0. So I'll be taking t equal to 0. So where t is nothing but your current iteration. Okay, and the max iteration is nothing but your maximum number of iteration. What you define as 500. Okay, so now we have gone inside. As I told you already, you can see the loop is started. This is what your loop is started. Now inside the loop, for each particle, you have to calculate the objective and you have to update the P best and G best. This is what they is the pseudocode, right? So now what I do for each particle, for I is equal to 1 to n. That is why n is nothing but your number of population, right? Number of particles. So for each particle, okay, we have to find a fitness. So I'll be taking my fitness. Fitness is equal to, okay, fitness is equal to what I'll be doing now. F object of position. So for each position, I have to find the value. I'll be telling you what it is now. Yes. So here you see, I'll be calculating the fitness for the objective function what I have created. Okay. So this f object is nothing but here I'll define it. My f object is nothing but my objective function. Is nothing but I'll just call my objective function. I just call my objective function. So you don't know because so far we have not created the objective function. So now, just to clear yourself, I'll just create now objective function. Okay. So to create the objective function, I'll be taking a function. My objective value is equal to some sphere because the problem is sphere problem. So I'll be taking my x is equal to this is. So here I am going to create my objective function. Okay. So now just look at this. What is your objective function? Just look at this. Sum of x square, right? This is what your objective function. So the same thing I'm going to create it. My objective function. Okay. So if you have any doubts, I'll just keep all. Yeah. If is equal to sum of, it's a vector addition. Sorry. This vector addition. So sum of square. Okay, that's it. Your function is over. You see, this is what your function, right? Just look at this. Your f of x is equal to sum of x square. So the sum of x square is defined. This is nothing but your objective function. Okay, so I'll just save it. I'll just save objective func. I just save this objective func. So this is what your objective function. Is there any doubts here? So like this, you have to create objective function for any of your problem. Okay, I just created the objective function. I just call the objective function through this variable f object, and now I'll be calculating the fitness for this f object. Okay, that is the fitness value for each particle I have to calculate. That is each position of the particle I have to calculate, so that I have done f object position of I comma. This semicolon is given because I'll be considering all the columns here. Okay. So you see that the fitness is calculated. If you have a doubts, okay, if you have a doubts, I'll just run this now. I'll just run this. Just look at the fitness value. Just look at the fitness is equal to 1.5 to the power 3. Okay, it's created now. Now what we have to do is, as per the step, as per the pseudocode, calculate the objective value is done for each particle is done. Next, update P best if required, update G best if required. Now we have to update both the functions. So to update it, first I need to compare my P best with the fitness what we have calculated. So for that, I'll just take if my P best is greater than fitness what we calculated. Okay, if the P best is P best of each population, so P best is greater than fitness, what we have to do is, so it means my P best value is higher than the fitness what you calculated. So the, obviously it's a minimization function, right? Then what will be the P best value is P best of I is equal to fitness. I'll just update it with the actual fitness what we calculated. Then same way you have to find the, you have to update the position of the position also we have to update. So the position will be equal to my position of I comma yes. So what I did, I just computed the fitness value for the objective function what I calculated. Now I'll be comparing this fitness value. I'll be comparing this fitness value with my P best value. If my P best value is greater than this fitness value, my personal best will be equal to fitness, and my personal best solution, personal best location will be equal to the current location. Okay. If this condition is violating, the P best will be whatever it is calculated already, that will be there. It will not update. Okay. Similarly, we have to update the global best also, because that's what the step, right? So update P best, update the global best. So now I'll be updating my global best value. So for that, again, I'll open another if loop. Okay. So if my G best is greater than fitness, what do you have to do? The G best will be equal to fitness. G best will be equal to your fitness. Okay. And your G best position will be equal to the actual position of the particle. That's it. Oh, sorry, end does not end. Just end it. Yeah. So now this step is over. This loop is over. For each particle, we calculated the fitness, and the fitness value be compared with the P best, that is personal best, and the fitness value compared with the global best. And based on the comparison, your P best and G best will be updated. Right? So you can just run it. You can check. So I'm just checking for each thing whether I'm doing it in the right way or not. Okay. So now you can see this is what your fitness value. This is what your fitness value. Now I just open the G best. You can see the G best is equal to 96. You see the fitness value calculated as 8.81. But you see the G best value is 96. It means that it is violating this condition. So the G best will be equal to whatever the G best already calculated. I just run once again. You just see the fitness values keep changing and G best values also changing. It's because of your random nature. Okay, again I'm running it. Just see here. Now you see here the fitness is 396. Now your G best is also 396. It means now it has gone inside the loop so that the G best value is updated as like what fitness value is calculated. Okay, so it's a simple understanding. I just ran it. Now what I do know, I just go to this loop. Okay, I'm just keeping this now. As of now, I'll just keep this because update inertia weight is there. As I told, the inertia weight I have taken directly, as W I have taken directly. Now, what I'll do is I'll go to this loop again. For each particle, you have to update the velocity and you have to update the position. So that I'll be doing it now. So again, you open the for loop for I is equal to 1 to n and at the loop. Okay, and inside the loop. Yes, inside the loop, what you have to do first, you have to update the velocity. So well, that is what the how to update the velocity. You know the equation, right? What is the velocity equation? I'll use this for formulas now. Okay, I'll use this formulas now. The velocity of next iteration is equal to, you see, the initial weight in the current velocity plus the cognitive component plus social component. So now I'll be using these equations. Okay. Yes, I'll be going inside. Yes, my velocity is equal to I comma. So I'll just calculate for each dimension also. That is also required for j equal to 1 to dimension. So another window. Yeah. So it means for each population and for each dimension, I'll just calculate my velocity. That's a meaning of it. So it is equal to your current W into your current velocity. I comma j. Yes, sorry, plus. Okay. So you can see what is that? C1 into R1 into personal best minus the actual position. Okay. So that I'll do C1 already we defined it into the random number. I'll take R1 is nothing but your random number. I'll take. Okay. Now we have to find the distance between the personal best and the global best. Okay. What is P best? P best position of I comma j minus x of, sorry, not x, position of, that is what your actual position, right? I comma j. So now you see that, just see, the cognitive component is over. You can look at this, C1 into R1 into the personal best position minus the actual position that we found it already. Right now, the social component we have to find. What is the social component? C2 into another random number into, okay. Now we have to find the global best distance. Okay. That is G best position minus position of, because G best means only one is there, so that we have to be very careful. Okay. I come on G. Okay. You see now what I did, I just created my velocity equation. Once the velocity equation is done, we have to update the position, right? So the position of I comma j is equal to the current position plus the velocity, what we calculated in the previous step. That's it. Your algorithm is over. Okay, you see the algorithm is over. Then finally it will give the best solution. So my best solution, best fitness is equal to G best, because always I'll be taking my G best is the best solution, and best position, I'll be taking it as G best position. That's it. So the algorithm is over. You can see as per the pseudocode it is created. Okay. So let me run it. If you have any doubts, please ask me. I'll just clear it. Then I'll just go for running this algorithm for a simple objective function while we are checking. Do you have any doubts? See, don't think that the algorithm is already available. We can take it and we can use it. So don't think like that. As I told, the algorithms need to be fine-tuned properly for your problem. If not, definitely you will not get the proper solution. So for that, we should understand how the algorithm is developed, how it is functioning. So then only you can fine tune the parameters. Okay, I hope it is clear. Okay, so I already created the objective function. So let me run. What will be the value? Let me check. Okay, so I found the problem where the problem is. Oh. Okay, I'll just take it. The G best value, I made a problem. I made a mistake here. So this will be for each dimension we have to find. Correct. Yes. Done. Okay. So can you see the solution? I think some questions. No. So actually, what we made mistake. No, I'm sorry. So one person is trying. they got same error. So the thing is, the error is because of this part. So we have to find the G best position for each dimension. So this need to be indexed properly. So that's what. So if you put it, you can easily find the solution. You can see. You can see now. I just break the equation so you can see. So that's it. You see. So if you want to see the convergence curve graph, okay. If you want to see the convergence graph, so that need to be defined properly here. Okay, C curve. That is convergence curve. So whatever you want it, you just give the name. So it is equal to the zeros of 1 comma dimension. Just take it already. I've done it. I'll just take copy paste it. Yeah, I'll just take it and I'll just paste it here, just for save the time. So again, already I defined. So I just want to draw the convergence graph. So initially I have taken my convergence is 0. Then after that, I'll just do that convergence of for conversion for each iteration. Each iteration is equal to my best fitness. I'll take it. Yeah. So once this is done, and at the end of the iteration, it will plot. So I'll just use a semi-log curve. So semi-log y of the CG curve, I'll just keep it. Okay, and you can easily find the convergence graph now. Sorry, maximum iteration. I just made a mistake, sorry. Okay, so this is maximum. Yeah, I think now it's right. Yeah. CG curve. You can see that the convergence graph. Okay. Let me check. Let me check. Why I couldn't be able to find it. Log y. It's there. We have a CG curve. It's done. It's not there. Iteration. Yes. Let me run it again. CG. Okay, okay. Sorry. I made a mistake here. Yeah. You can see the CG curve, the convergence curve. Okay, you see? That starts with the initial solution, some value. Okay, for each iteration, the value is progressing. It's progressing. And at the end of the 500 iteration, I got my solution as 1.3870 e power minus 218. So actually to say for this particular problem, the value should be 0, correct? The fitness should be 0. That's what, because what is your objective function? It's a minimization function. As I told, it is sum of x1, that is x1 square plus x2 square. So the LBUB is defined. It will vary between -100 to +100. And you can see the best position also. The x1 is equal to 1.12 e power minus 109, and x2 is equal to 3.3 e power minus 110. So the eigen positions are 0, 0, so that you'll be getting 0 value. So what I do, I just increase the number of iteration to 1000. I check it is reaching 0 or not. You see that? You see my G best to 0 now. So yes, it could able to find the 0 here. So the respective position of the particle is this one. You can observe it. Okay, so minus 4.27 e power minus 163 minus 1.29 e power minus 163. Okay, so this is what the thing. So this is how the for PSO algorithm solves a numerical problem. Okay, so here I'll just show you the impact. I'll just show you the impact of the W everything. Okay, so I'll just take now. Initially, you kept your W is equal to 0.1. I took my W is equal to 1 now. Now just look at it. Just look at it. I'll run it. Okay. Now you just see my G best is 5.3487. You can see that my G best value is 5.3. Actually, to say you should get 0, but my G best value is about 5.3487. So this is not correct. So it means that my algorithm is highly explode. Okay. Highly explode. So now I'll just change the value to some 0.5. Yes, I think it could able to reach some value. See that minus 65. But if I go to point 1, if I go to point 1, you can see that it could able to get e power minus 196. So the value is better. So you may think that, okay, why not 0.01? Yes, you can try this. As you can see that my value is minus 251. Yes, again, I'll keep minus 0.01. You just see that it is almost the value saturated. Okay, so the impact is very less. So I can say W is equal to 0.1 will be the best one. So now what I will do, no, as I told, I'll keep my global best value 0. So if I take global best only with personal best, the values will be updated. Now you just see here, my G best value is 86.8041. My best fitness is 86. It's very poor, right? 86 we are getting. It's very, very poor. Now you see for second iteration, 805. Then for third iteration, yes, I'm getting 609. So for each execution, I'm getting different value, but it is not equal to 0 because I consider my global best is 0. Now what I'll do, I'll keep my personal best as 0. If I keep my personal best to 0, again you can observe what will be the value. You see that, yes, it could able to reach minus 278. It is also a good one. So it completely avoids the personal best. It looked like best to one. Maybe the problem is simple, but for the complex problem, no, for the complex problem, you have to consider the decision taken by the personal best also. So in order to have the proper balancing, I have taken C1, C2 both values equal to 2 so that I'm getting some kind of minus 2 or 6. Okay. So this is what the impact of your C1, C2. And now here what I did now, I have taken my W is equal to constant, right? So I'll take my W is the adaptive one. Okay. So that I'll be taking the minimum weight is 0.1 and the maximum weight is 0.9. I'll be taking it. Okay. So now I'll just adopt it. So I just copy the adapt equation. Already I have written it. So I'll just copy paste it here so that we can use it directly. So as per this, you can see it as per the pseudo code. Yeah. So I'll just update the inertia weight. I'll just update the inertia weight. So now here, I'll just update my inertia weight. My W is equal to this W max. I will define it. Okay. And this is T and W max, W min. So we have a lot of equations like this, So only thing is you have to find the proper equation for updating the velocity, inertia rate. Okay. You can see that my inertia is now throughout iteration. See, for each iteration, the W value is not the same value. Okay. Now I run this algorithm. I'll just try to see what will be the values now. Just see here, my best fitness is 3.1 e power minus 77. So compared to the previous one with constant weight, I got good solution. But for this adaptive equation, I got a bad solution. So that's what every time when we use any algorithms, we have to, it doesn't mean that always this adaptive weight will give the best result. Maybe this adaptive weight will give the best result for one of your problem, but not for this problem. Okay. So in this way, you can easily, improve the algorithm. Okay, this is one of the way to improve the algorithm. You can find one new equation, new adaptive equation, and you can say the novelty is on the inertia weight side, so that I can improve the exploration and exploitation capability of my PSO algorithm. Okay, so I hope you understand how the PSO algorithm is working, right? So if you have any questions, you please ask me. Else, I'll move on to the next objective function, that is parameter estimation problem. The algorithm is same. I'm not going to change the algorithm. The algorithm will be same. Okay. I'm just going to formulate only the objective function. Please tell me if you have any problem. If you don't have, please that also please acknowledge so that I can start. Any doubts here? Yeah. So someone has asked one question. This considered as a continuous problem. Am I right? Yes. Are we using discrete method for scheduling problem? What are the things going to be changed here? Yes. Okay. It's a very good question. So so far what we discussed is completely, it is a continuous optimization problem. Okay, because you see that the positions are updated continuously. The position of the variables are updated continuously. But we have certain problems. Even for example, you take a unit commitment problem or the scheduling problem, what one of the fellow asked. So the scheduling problem, for those problems, we need the discrete variables, that is the binary variables are required. So when we need to solve the binary problem, we cannot use this continuous algorithm. We have to create a binary algorithm. Okay, we have to create a binary algorithm. So to create a binary algorithm, what you have to do, you have to transform all the continuous variable to the discrete variable with the help of some transfer functions. Okay, so we have a transfer functions like, V-shaped, S-shaped, U-shaped, T-shaped, okay, tapered shape. So like that, so many transfer functions are available. Okay, with the help of the transfer functions, you can easily convert the continuous variable to the binary variable, and you can use the algorithm to solve the binary problem also. It's possible. We need to create a binary algorithm just by transforming the continuous variable to the binary variable with the help of the transfer functions. We have so many transfer functions. Okay, so many transfer functions are available. So you can use any one of the transfer function. You can transform the continuous variable to binary and you can easily solve it. So since that is not the scope of this discussion, okay, if time is there, I'll just tell you how to convert the PSO algorithm to binary algorithm also. Okay, so let me finish as per today's agenda. If time is there, we'll discuss how to convert to binary. Yes. So another question, to apply PSO, is it needed to know the mathematical model of the plant? Obviously, because the PSO, what we have created is an algorithm, right? The plant model, that is what your objective, right? So the objective obviously have to plan it. So for example, simply you take one DC motor speed controller is there. Okay, for DC motor speed control unit, you should know what is the transfer function of the DC motor. You have to create one Simulink model. You have to create a Simulink model. So then for the Simulink model, you should know the plant transfer function. Then there we'll introduce one PI controller or PID controller, right? So only the PID controller values will be tuned with the help of PSO. But you need a model, you need a mathematical model of the particular plant. Without that, you cannot solve it. Okay, if you want, I'll just show you one thing. Okay, so since you asked me, I'll just show you something. Okay, yes. Okay. Just create this. Yeah. So now if you look at this, I just created the model. Okay, it's only a simple speed control of DC motor. Okay, so for this, the plant is created. Actually, the mathematical, the transfer function model is created. Okay, I'll just show you here. You can observe it. Yeah, you can look at this. Just look at this. This is what your transfer function model of your DC motor. Okay, and this is what your transfer function, 15 divided by 1.08 s squared plus 6.1 s plus 1.63. This is your plant transfer function. Okay, and this is your PID controller, and you can just look at inside. Usually we'll keep the KP value, KI value, and PD value here. But here, what I'll be doing, I'll be I'll be computing PI, PP, KI, PD values with the help of the algorithm. And based on that, it will calculate, it will tries to find the speed of, it will tries to match the actual speed of the induction, display DC motor, whatever it is. Okay. Again, for this, we have to create an objective function. Without objective function, we cannot do it. So to create an objective function, obviously, this model is required. Without this model, we cannot proceed. So I hope this is clear. So possibly, if time is there, I'll just show you this simulation also, DC motor simulation also, if possible. If everything is okay, I'll just move on to the next problem. Shall I move on to the next problem?
Yes, doctor, we have another 1 hour, so you can.
Okay, no question. Yes, sir. Yeah.
Yes,
Yeah,
doctor,
yeah, okay.
you can proceed.
Yes, yes. I'll just proceed it. I'll just proceed it now. So now I just go to the parameter estimation problem. Okay, maybe due to the time constraint, I'll just go to the single diode model. Okay, so as I told, for single diode model, what we should know is we should know this equation. Okay, and we have to use this equation to solve the entire problem. Okay, you just remember this equation, so it's very much required. Okay, yeah. So let me move on to. I just open another new file. Okay, so before going to the new file, what I do know here, I just limit. I'll give the limitations. Okay, just save this file as graph for PV. Okay. Yes, I'll just save this file as PV. So now again, I'll just give some other file name. So fitness, I'll just give it other file name is fitness. Okay. And as you know that for single diode model, there are 5 dimensions, right? So there are 5 unknown variables. So my dimensions are 5. Okay. My dimensions are 5. Then now we have to define the decision variable for each parameter. Okay, so I'll just define all the parameters now. Okay, you should know these parameter values. Okay, so first I'll be defining the lower limit for the photocurrent. I'll be taking it as 0. Okay, and the next one is your what we can take, yeah, saturation current we can take, that is also the lower limit is 0. The next series resistance I'll be taking it as 0, and the shunt resistance I'll be taking it as 0, and the diode ideality factor. So you know the diode ideality factor of the PV cell will be varies between 1 to 2, so I'll be taking 1 as the lower limit. Okay, yes. Now the upper limit we have to give. So you see, for our discussion, I'm going to derive the parameter of the RTC France silicon solar cell. Okay, RTC France is a France silicon solar cell. Okay, so that cell, it's a very small cell. It is a benchmark cell, I can say. Okay, so for that cell, the upper bound we can say, because the maximum current will be 0.7608. That is what the benchmark value. So what I'll be doing now, I'll be taking my upper bound as 1 photo current, and the next one is the saturation current. So for this saturation current, it is not exceeding 1 microamp. So I'll be taking 1 e power minus 6 is the lower bound, upper bound for the saturation current. And the next is the series resistance. So series resistance, I think it will not be more than 0.5 ohms. Okay, it will be varying between 0 to 0.5 ohms. Okay, and the shunt resistance, I hope. So I think what I have taken, yeah, okay, 100 ohms I have taken. So my shunt resistance will be varying between 0 to 100 ohms. Okay, and the diode ideality factor will be vary between 1 to 2. So these are all the limits we have to give. See, if these limits are not proper, your algorithm will give poor results only. Okay, so what I did, I have given the lower limits for all the 5 parameters. I have given the upper limit for all the 5 parameters. It's done now. Okay, so now I just create the objective function. Okay, taking function objective is equal to SVM model, so single diode model of X. I'll take it and I just send this function. Okay, so now when you look at this equation, see that some constant parameters are there. You see the Boltzmann constant is there, the temperature is there, then electron charge is there, right? So all these need to be defined properly. And before that, I'll just assign all my unknown variables with the decision vector. So the first unknown variable is I phase, the photocurrent is the unknown variable. So that is nothing but my first variable, right? X of 1. Then the second, what we have taken, ISD we have taken, that is saturation current. So that is X of 2 is my saturation current. Sorry. X of 2 is my saturation current. The next is RSC, series resistance I'll be taking. That is nothing but my third variable, because that's what we define. No? Like that only we have defined here. You can see. First is your photocurrent, the second is diode saturation current, and third variable is your series resistance, and fourth one is parallel resistance or shunt resistance, and diode ideality factor. So in that way, I'll be taking everything. Okay. So or SH is equal to X of 4. Fourth variable, I'm just mapping it. Then my diode ideality factor, I'll be taking it as A, that is X of 5. I just mapped all my parameters with the decision variables. It's done. Okay. After this, what we have to do, we have to define all the constants. So I just took all the constants already. So I just take everything now. So Q is the electron charge. So that is equal to 1.6 e power minus 19. And K is it's a constant. You can take it from any of the papers. So I'll just show the paper of mine. I'll show that you can easily take it. So K is your absolute temperature, sorry, a Boltzmann constant. It is 1.38 e power minus 23. It's constant again. And temperature, this need to be defined in the Kelvin. So this 273.15 plus 33 degrees. So because the whatever the data set we have, it is generated at 1000 watt per meter square and 33 degrees Celsius. So the temperature is taken as 33 degrees Celsius. Okay. And that will be converted to Kelvin so that we added 273.15. This is done. Right. The next one, what we need is we need data set. Okay. We need a data set. The data set in the sense data samples. Okay. So as I told, this RTC France Silica cell is a benchmark cell. Okay, they have the open set data. I'll just show you the open set data. You can see this is what the open set data. You can see the first row is your voltage and the second row is your current. Okay, so they have taken these voltage and currents at a temperature of 33 degrees Celsius and irradiation of 1000 watt per meter square. So this data set is available. If you want, I'll share it with you people so that you can practice it. Okay, so totally you can see totally there are 26 data samples are there. Okay, 26 data samples are there. You have taken it. So now from this data set, what I'll be doing, I'll just read the data. Data is equal to load. What is the file name? I can say .txt. Yes, so I just read the data here. Okay. Yes, so suppose if you want to know here, you can see that just load it. Okay, it's not in the current folder. So what I do is I'll just add this to my folders. Yeah. Okay. So yes, you can see the data is created. You can see the data came in the workspace. So this is the first row is your voltage and the second row is your current. Okay. Yeah. Okay. So now I'll just split my voltage and current. Okay. So VPV is required. So VPV is nothing but data of 1. Right. Then IPV is nothing but already we read the data. So from the data, I'll just call the second column. So sorry. Yeah. Yes. So now I'll just put this. You can see that whether the values are extracted or not. Yes. You can see the VPE. Oh, sorry. Column and row. Just interchange it. So this is 2. And this is, yeah. So I just interchange the column and row. Sorry. That's correct. Now you can see that VPV is extracted. Okay, this is what your VPV and your IPV. Yeah, IPV is also extracted separately because for my equations, this is required. That's what I have it done. Okay. So now the constants are defined. The variables are called from the lower bound and upper bounds. Okay. Now I'll be writing I estimator. I just want to estimate my current. I estimate. Okay. IE is nothing but my estimated current. What is the equation? I phase, right? I phase, that is I photo minus, correct? Then ISD into exponential. Yes. What is that? Q into VPV plus IPV into RC divided by J into K into T, yes, minus 1. This is what the equation we have written already. Okay, see that ISD into exponential Q into VPV plus IPV into RSC divided by AKT minus 1 minus VPV plus IPV into RSC divided by, okay, I'll just formulate the equations properly, or else it will be a problem. Yeah. So this is divided by RSH. Yes. The current will be estimated like this. You see, it's easy, right? So I think maybe some problem is there. Invalid. It is invalid. Okay. So Q into this divided by this. So open the bracket so that this will be closed. Yes, correct. So this is what your estimated current. Okay, so now what your algorithm will do is it will compute the IE by considering the variables what we have, because these are all the experimental data, right? For each experimental data, okay, it will compute the current. Okay, once the current is computed, what we have to do, we have to find the error, right? What is your error? The error is nothing but I estimated minus IPV. Correct. So estimated current minus IPV you have to find. So once the error is done, then we can easily formulate your objective function. What's your objective function? Your objective function is nothing but the root mean square error. Okay. So it is nothing but the square root of 1 divided by your number of data samples into the error square. That is what your equation, right? So that I just copy paste it here. Okay. Yeah, I just copy pasted. You can see I have taken the right side here. So square root of sum of error square, okay, divide by 26. Why is 26? 26 is because my number of data sample is 26. Okay, and this is actually, you see that it is a array matrix, so obviously I have to keep this dot. Okay, so now if I use this equation, no, yes, I can easily derive the equation, my objective function. I just save it. I can see. I just save the numerical, so I'll just save it here itself. Fitness. That's what my equation I have written. Yeah. So I have written the objective equation for solar parameter. Now what it will do is it will try to find the parameters. Can we run it now? As I told, no other changes, nothing I'm doing. Okay. I'm just going with the simulation now. Okay. So I just run the simulation, just check it is okay. Yeah. Yes, it's running now. Yes, it is calculating. Yes, it could be able to find the value now. The screen is not illuminating like this.
Doctor, sorry to interrupt. Is it possible to share the code?
What's it?
The code, the you are using the code. So can you please share in the chat box?
Yes, so if someone wants it. Yeah, I can set the txt file. Yes, I'll just share with you. Okay. Yes, I'll just copy. Yes. Okay. The chat box. I think attach, can you attach? Yes, it's possible. Yeah. This. Yeah, I think it's shared now. You can take it. You can take it now. Got it, Nazar? Anyone can respond, please. Yeah, yeah, okay. Yeah, okay. So you see that it could able to find the best position. You see, it could able to find the best position, and the best of fitness is about 0.063. And the best position, you just look at this. Just look at this. This is my oil phase, that is a photo current, and this is my saturation current, and this is my series resistance, and this is my shunt resistance, and this is my ideality factor. Now you just look at these values. You just look at these values. Is it correct? Is it within our bound what we have defined in the algorithm? I think you see what we kept is the photocurrent can be vary from 0 to 1. Yeah, it is within the limit. Yes, correct. Then the saturation current can vary between 0 to 1 microampere. That's what we kept. But you see, this is giving some random value. And you see that RS is also is giving minus, and RSH is also within the limit. But you see the ideality factor is giving some some rubbish value to show you. Right. So this is what the problem of PSO algorithm. So whatever we created is a basic PSO algorithm. Okay. It couldn't able to find, because the problem what we have taken is a highly non-linear problem. So the PSO failed to find the best solution. So I can say the completely the values what it is extracted, well, the value what it is computed is, it is completely out of the bound. I have given the search space, but it just gone out of the search space, and it took some value and calculated the objective and it has given the value. So obviously it is not acceptable. It is not acceptable. So if you see the benchmark value for this particular problem is 0.7608 is the benchmark value, and this is will be about 0.3 e power minus 7. Okay, and this will be about 0.03 or 0.4 it will come, and it will be about some 25 to 26 will be there, and this will be on 1.28 something it will be there. So that is what the benchmark value for this particular problem. But you see the PSO completely failed to find the proper value. So this is what I told. Okay, for the benchmark problem, for the numerical problem, we got good result. We got very good result for the numerical problem. But when we apply to real problem, you just see the PSO has failed. So now what we have to do? Okay, so it is going out of the boundary, right? It is going out of the boundary. So what we have to do is we have to make the algorithm to find the solution within the given space. Yes, any questions? Yeah, okay. So we have to allow the algorithm to find the solution within the given search space. So for that, what we have to do? Okay, what we have to do is we have to provide one boundary handling mechanism. Okay, we have to provide one boundary handling mechanism so that the algorithm will not find a solution outside of the boundary. Okay, so one of the simple boundary is the temporary boundary mechanism. That's what is used here. I'll just copy and paste it in my code. I'll just explain this code now. Just focus on this. Yeah. This is one of the boundary handling mechanism. I just took some variable, okay, flag for UB, that is one variable. Okay, if my position of the variable is out of my upper bound, okay, and if my lower bound is out of my, if it is less than the lower bound, whatever I have given. So what you have to do is they have to update based on this equation. Okay, that is my position of the variable is equal to position into the flag for LB and flag for UB, okay, plus UB into flag for UB into LB into flag for. So this is one of the boundary handling mechanism. Okay, we have this, you can find it in all the meta heuristic algorithms. Okay, you can find mostly the people will go with this temporary boundary handling mechanism, but we have so many boundary handling mechanisms are available to improve your algorithms. Okay, so I just kept only one simple boundary handling mechanism. Now I'll try to run the algorithm. You see how the values are now. I'm just running it now. Yes, you see that simply I just kept that one. You can see it is within the limit. Can you see? It is not out of the boundary. It is not out of the boundary. So now it could able to find the result within the boundary. Yes, still my values are not correct because you see the best fitness is 0.2229. Actually, to say the benchmark value for this particular problem is 9.8602 e power minus 4 is the best fitness for this benchmark problem. So again, there is a problem. So where the problem is, here, the velocity, it is moving like anything. I think some questions came. Yeah. So the problem is here, the velocity is uncontrollable. It is going somewhere and coming inside. So for that, what I do, I just want to control my velocity. Okay. So for that, I'll be taking my maximum velocity equal to 10, not 10, I'll take 5 because 5 unknowns are there. So I'll be taking my maximum velocity is 5. Okay. So now what I will do now, I'll just compare the velocity with my maximum velocity. Okay, so that I'll just copy and paste this here. Okay, where is the velocity vector? Yeah. Here it is. I'll just tell you what I have done now. Okay. Okay. This is also need to be in the, yeah, that. So now what I did now, I just added few more steps extra to improve the algorithm. I just want to control the velocity of my algorithm. Okay, so for that purpose, what I did now, whatever the velocity we are updating, I'll be comparing my updated velocity with the maximum velocity what I have defined already. Okay, I think like a small bit, so yeah. So for each velocity update, I'll be comparing with my maximum velocity. Okay, if the computed velocity is greater than the Vmax, you have to transform your velocity equal to Vmax. So it is nothing but there we have defined right 10 kilometers and 20 kilometers. There we have restricted. Here we haven't restrict. So to restrict it, what I did, I just used some additional 4-5 lines to restrict my velocity. Okay, now I just restricted my velocity. Now what I'll do now, I run the algorithm once again. Yes. Okay. So still it couldn't able to find the best results. Still it couldn't able to find the best results. So what I do is I'll just go with this one, the adaptive weight. Okay. See, now the fitness is only 0.229. It's not good. Actually, to say it's not good. So I just employed the this one. What is that adaptive weight? Okay. Let me check. Is it giving the best result now? You can still it will be able to give the best result. So I can say my PSO is not good algorithm for this particular problem. Okay, so not only with the fitness, I'm saying the PSO is not good. Okay, I'll just show you all the things which is required for to analyze if my algorithm is best or bad, poor or good. Okay, so for that I just just send all my variables globally. Okay, just to plot the waveforms. Okay, so I just estimate is required. Yeah. Okay, so now here I'll just go to the draft. Okay, I'll just call all my global variables here. Just for plotting, I'm just doing this extra step. Okay, so IPV and I underscore E. Yeah, I'm just calling all the global variables, whatever I define the fitness. Okay. So now with that variables, okay, I'm just going to do the calculations here. See here, I just want to plot VI characteristics and PV characteristics. Okay. So now what I'll do now, I'll plot VI for the experimental and for the realistic one and whatever we estimated. Okay. Then similarly, I'll PV characteristics also I will draw. Okay. So for that, I'll just calculate the power. So I'll just calculate the power. Power is equal to, that is the estimated calculated experimental power is equal to the experimental voltage and the experimental current, and the estimated power is equal to voltage into the estimated current. I just done the power calculation and I just plot it. Okay. And I will tell you during the iteration, how my positions are updated. So maybe just for the time sake, I just comment it now. Okay. I'll just show you only the waveforms. Okay. IV and PV waveforms. You can observe it now, how it will be. Yes, you just see. I think you can able to observe, right? Yeah, okay. You see now PV characteristics. I'll keep it. Just look at this. This blue color line is the experimental IV curve, and this red color one is the estimated one. You just see the curve fitting between both the things. Lot of gap is there. So I can say the PSOS completely failed to find the failed to find the proper value. If the values are proper, definitely it will be the best result. So for that purpose, what I will do now, or what I will do is I just improve the maximum iteration to 1000, okay, and number of population to 40, because that is the algorithm performance is also depends upon your maximum iterations and the number of populations. Okay, I just kept it now. Okay, let me check how it is now. Yeah, see, still it is failed. Still it is failed. I couldn't able to give the proper result. You can see that. You see, though I am doing whatever the thing I'm doing it couldn't able to find the proper result. So I say the PSO is not the best algorithm for finding the parameters of the PV, but I did small adjustments in my code. Okay, I did small adjustment in my code. Okay, I'll just run the code what I developed already. Okay, if you want, I'll share it. It's not a problem. Even I just kept it the MathWorks also. You can take it. Okay, so I'll just run the PV what I just improved. Okay, I'll just show you. You just see the performance of the same PSO with improved version. Okay, just see now. Just see now. It could able to almost, this is almost matching here. You can observe it. You can observe my experimental curve and my estimated curve is almost matching it. Okay, and I told you one more waveform. No, just see here how the photo current is varying. How the photo current is varying during my iteration. So that is also kept here. Okay, so these are all the very important the facts you have to understand from this problem. Okay, so I hope this is clear. I hope this also implemented. Let me run the algorithm once again, because still I could be able to find the best result. Max is also commented. Yeah. So that the code what I developed, I just share it with you. Just look at the code. I just made one very few modifications. Okay. So you can see now. I told you, the benchmark value for this is about 9.86. Okay, so here you can see the fitness. It could able to find 0.02. It's okay, somewhat okay, acceptable. You see the best G best position 7806. My current is 0.002, and still you could see that my series resistance is going out of the boundary, and here you can see that RSH is within 100 ohms, and You see the diode ideality factor is also going out of range. So whatever the adjustments I do, I'm facing a problem. Okay, so let me run one second. Because yesterday it was a good result, so just want to see. Because I told you, it's completely all the algorithms are, it's completely of randomized algorithm. For each run, you will get only different results. Now, initially we got 0.02, but here now you see the best fitness is 0.002. So now the fitness is almost increased, and you can see the matching between PV and IV curve. It's complete 100% matching. You can see now. The experimental curve and the estimated curve, it's completely matching. Okay, so this is what the problem with the stochastic algorithm. It will give the best results, but to get the best results, we have to run the algorithm multiple times. So what that optimization society is saying that to get the best result, you have to run the algorithm 30 times minimum to get the proper results. So if you run the same algorithm for 30 times individually, you can find the best result, as I told, 9.8602 per month. So that result you can be able to find it. Okay, so I hope this is clear, right? If you have any problem, please tell me, or else I'll just move on to the next one. So whatever I developed, okay, I'll just share it with you. You can use it. Even I just kept the code. Okay, I'll just show you where I kept, or else I just share. I just share the link with you. Okay, and you can take it. Yeah. So this is for STM. I already developed it. Okay, so I'll just keep this code to you. You can take and you can test it. This is for Jaya algorithm. Okay, if you want, you can take it and you can use it. Okay, a few more codes also are kept. Or yes. So one of the question I could see, how can we check that it is the best solution? Yes. See, if the problems are, for example, if the problems are already existing, okay, already existing, then you can find the benchmark value, what it is. If the problem is new, if you are developing the problem means, what you have to do is you have to take minimum 10 to 15 algorithms, apply same 10 to 15 algorithms for the same problem, and run each algorithm 30 times. You take the results of each algorithm, then you find which one is the best. This is the only way to find the best result. Okay, so and one more thing is that for each thing we have to have some performance metrics are there. So even for this PV parameter estimation problem also, apart from RMSE, we have some other performance metrics, like the statistical data are available, the minimum value, maximum value, mean value, standard deviations, the runtime of the algorithms. Okay, so runtime of the algorithm. Okay, then not only that, for parameter estimation problem, we have the absolute error, mean squared error you can find, then relative error you can find. Okay, so you can find so many performance metrics. Then you just compare the performance metrics of each algorithm. Okay, then if you have 10 algorithms, which for all the 10 algorithms you find the performance metrics, and you just see which one is best. Then whatever the best algorithm is there, maybe that result will be the best result. So with that only you have to do it. Okay, so here even for this problem, what I told, the 9.8602 is the best solution because it is a benchmark problem. So I know this is the best result. So, but for the problem, what you're going to create may not have the benchmark value. So the only way to analyze the result are best is run the algorithm 30 times for 10 different algorithms and take whichever is the best value. That will be the benchmark value. With that, you just go ahead. Yes. Yeah. Okay. So I think everything is okay from the PSO side, right? I'll just move on to the next one. I just quickly tell you how the Gray Wolf algorithm is created, and the same testing I'll just do with a Gray Wolf algorithm also, so that you can easily understand how the Gray Wolf algorithm is created and how it is applied to the same problem. You see, why I have taken the particles form optimization algorithm is, as I told you already, most of all the meta heuristic algorithms are very much similar to particles form algorithm. If you understand the particle swarm optimization algorithm in a better way, you can also design your own algorithm. Just we need inspiration. You can, with any kind of inspiration, you can design any kind of algorithm. Even I just want to share it with you people. We know as electrical engineers, we know the RC transient response of circuits for the DC circuits, right? If we give the DC supply to the RC circuit, yes, you'll be having the voltage response. So in the voltage response, you'll be having steady state response and the transient response. So we just mimicked this transient response and steady state response as an algorithm. And recently we have introduced an algorithm called RC optimization algorithm. That is resistance capacitance optimization algorithm. It is recently proposed and recently published algorithm. Okay, soon we'll post the code in the MathWorks. Once it is done, yes, I'll share it with you people so that you can start using it. So likewise, if you have any kind of inspiration, you can design one new algorithm. Okay, just you should know the concept of the algorithm. So as I told, once you understand PSO, you can design any kind of algorithms. Okay, yes. So with this thoughts, I'll just go to the next one, the gray wolf optimization. I'll just quickly go through this. Okay, I don't want to discuss much about it because of the time constraint. Yes, so the gray wolf optimizer, this is developed by the scientist called Syed Ali Mirjalali. Okay, he is one of my collaborator as well, so we have done a lot of collaboration with him. Okay, and he has developed this algorithm in the year 2014. In 2014, it is developed, and he actually shared the code in open source. So because of that, he could able to get 10,000 citations within 7 years. So as we know, the PSO is having 75,000 citations, but this 75,000 citations, it's because it is a long time back it is introduced. But now just 6-7 years back, this algorithm was introduced, but he could able to attract more people with more citations. Okay, so the algorithm is very simple. As I told, it is also almost similar to the PSO. Okay, I'll just tell you what it is. Okay, so the gray wolf optimizer, so it is a completely a population-based algorithm, as we discussed earlier. It's a population-based meta-heuristic algorithm, and here the inspiration is the leadership hierarchy and the hunting mechanism of gray wolf. Okay, leadership hierarchy. So usually the gray wolf will be lives like a troop. Okay, in the troop, one higher level people will be there, middle level people will be there, middle level groups will be there, and the lower level groups will be there. So we have some kind of leadership hierarchy. Then it is having one unique hunting mechanism. Okay, so based on that, this algorithm was created. Okay, and as I told, it is proposed by Mirjalali in the year 2014. Okay, so here, as I told, gray wolves prefers to live in a group. We call it as a pack. Okay, in each pack or in each group, 5 to 12 group members will be there on average. Okay, so now you see, as I told, the inspiration is based on the social hierarchy and the hunting mechanism. Okay, you see, this is what the social hierarchy. You see, the alpha wolves are there, beta wolves, delta wolves, and omega wolves are there. So the alpha wolf is nothing but the leader. Okay, he is a leader. He will be giving order to all other wolves. Okay, the beta wolf is the middle of, that is the next powerful person than the alpha. The alpha is the top powerful person. Then after that, the beta wolf will be there. What beta wolf will do is he will get the information from the alpha wolf, and he will be giving the information to the delta and omega. Okay, and the delta wolf is nothing but these wolves will be entered into the hunting process. Okay, actually the alpha and beta, they will not do the hunting. Only the delta wolf will do the hunting process. Okay, and sometimes omega wolf also will do. The omega wolf is the lowest priority wolf because there, the most aged wolves will be there. Okay, so most of the time the aged wolf will not participate in hunting. Okay, sometimes it will be considered. So that's why in his algorithm, what he has taken, he has taken only alpha, beta, and delta wolves. He just omitted omega wolves. Okay, so that's what the hierarchy. As I told, the alpha wolf is the leader, and he will be giving all the orders to the other people. And as I told, the beta wolf, he'll be getting the orders from the alpha, and he'll be giving to the other wolves. And suppose if the alpha wolves getting older, then the beta wolf will be the leader finally. Okay, likewise, it will be a cyclic process will be happening. Okay, then the third level, as I told, the delta wolf, as I told, these people will participated in hunting. Okay, and we have the omega wolf also, but for the omega wolf, as I told, they will not consider it for any of the iterations. Okay, so as I told, only 3 wolves will be considered. We just see the hunting mechanism of the gray wolves. So this is what the hunting mechanism, as I told you, see, the wolf will be like a troop. It will be like a group. Only can see in each group, maybe 5 to 12 wolves will be there. You can see that there are the wolf troop is there. Okay, and how it will do hunting, you know, first it will tries to find the prey. Okay, here you can see the buffalo is the bull is there. Okay, so bull is the prey for this. Okay, now the wolves are going to hunt this prey. Okay, so first what they will do, no, they will chase the prey, and it will approach the prey. Okay, by tracking it. Okay, then once it tracked it, what it will do, no, it will harass the prey. Okay, it will keep disturb the prey. Okay, then after that it will encircle the prey. That you can observe here, it is harassing it. Okay, then it is you can see it is all the wolves are completely encircling the prey. Okay, once it is encircled, so you see that prey cannot move, because once it is encircled, the prey cannot move. So because of that, the hunting process will start. So first it will attack, and will finally it will hunt. Okay, this is what the wolf hunting mechanism. So what he has done is he just mathematically modeled that the social hierarchy along with the hunting mechanism to create the gray wolf optimizer algorithm. Okay, so as I told, the mathematical modeling, you see that this is what the mathematical modeling. Okay, you see that there are few equations, very few equations are required to understand the GW algorithm. As you know, the PSO only 2 equations, but here more than that, some equations are there, but the equations are almost similar to the PSO algorithm. So here you can see first a D matrix will be found. So the D is nothing but the distance between the prey and the wolf. Okay, here you can see that XP is a prey and X is nothing but the wolf position, and XP is nothing but prey position. And here they have introduced one constant vector called C. Okay, so this C is used to control the exploration capability of the GW algorithm. Okay, this is a distance. Okay, now the position update of the wolf will be based on my prey position minus the distance what we have calculated already. So distance is already calculated, and we have introduced another parameter called A. Okay, so why this parameter is done? No, it is again to control the exploration and exploitation capability of the GW algorithm. If K is less than 1, the the wolf is moving towards the prey. If it is outside, the wolf is moving out of the prey. Okay, maybe you can, I'll just show you some pictures so that you can easily understand. Okay, so as I told, this A and C both are the coefficient vectors, and these are the random vectors. Okay, you can see the A vector is created by 2 into small a vector into R1 vector minus A vector. So this R1 is again nothing but a random number. Okay, this A is a number, it's a coefficient. It will be linearly varied from 2 to 0 throughout the iteration. Okay, you can see that it will linearly vary from 2 to 0 throughout the iteration. And C is completely of a random number. You see, just look at this equation. It's completely similar to your PSO equation. You can observe it. That's what I told you. If you understand the PSO better, you can easily match any of algorithm with PSO. Okay. So with this basic equation, you see, first they will find the distance. Okay, and they will update the location based on the distance. This is for one wolf, but in our gray wolf optimizer, they have considered 3 wolves, right? Alpha wolf, beta wolf, and delta wolf, right? So they'll find the position of alpha, and they'll find the position of beta, and they'll find the position of delta. Okay, so now we have 3 positions. Now our final position is the average of all 3 positions. Okay, that's what here you can observe it. You can observe it. See, the X1 is nothing but alpha wolf position, X2 is nothing but beta wolf position, and X3 is nothing but delta wolf position. Once you know the position of all the wolves, then you can take the average. That will be the final position update of your gray wolf optimizer. That's it. It's very simple, right? So it is completely, I can say it is similar to the PS1, but with few extra parameters, I can say. Okay, so now here I told the exploration exploitation. You see that the impact of capital A. If the capital A is less than 1 and greater than -1, you can see that the wolf is moving towards the prey. Okay, suppose if your A is greater than 1 and A is less than -1, you just see that wolf is moving out of the prey. So in this way, you see, this is called exploitation and this is called exploration. So that's what I told, that with the help of the parameter A, we can control the exploration and exploitation of the GWO algorithm. Okay, so in this way, they have done the modeling. Okay, I just don't want to discuss all these things. Now just go to the pseudocode. Okay, so as I told you in the PSO, the first thing is what? We have to initialize the algorithm parameter. Once the algorithm parameters are initialized, what we have to do? We have to generate the random population solution and we have to find the fitness of the solution. So here there are three fitness solution, right? Because we have considered three wolves, that is X alpha, X beta, X delta. So for all three wolves, we have to find the random population solution. Once it is done, then it will enter into the main loop. So here we used while loop. So if the current iteration is less than or less than maximum iteration, this loop will be continued. So now for each population, we have to update the position. Okay. Then after updating the position, there what we did, we updated the personal best and the global best, right? In same way, here also we have to update the best position of alpha, beta, and delta. Once it is done, there we updated the inertia weight, right? So here we have to update the small a, capital A, and C. Then after that, you have to find the fitness value. Then we have to find X alpha, X beta, and X delta. Then we have to take an average of this. Then it will be continued for all the iteration. Then finally it will end off the loop. Okay, it will be terminated and it will come out of the loop. Then finally it will return the best value. Here, the best value is considered the alpha position and the alpha fitness is considered as the best solution. Okay, because that is the top level hierarchy, so that it will be only alpha position and alpha fitness will be considered as the best solution. Okay, so this is what the pseudocode. Okay, I'll just quickly show you how the GW was created. Okay, so that, and I'll just apply the same problems and you can see if the GW is better than the PSO, that you can observe it. Okay, so what I do, I'll just go to the code. Yes, I just open GW algorithm here. You can see that the same, you see the formats are almost same. The formats are almost same. Okay, you see, I just define all the algorithm parameters and the algorithmic parameters A equal to 2 and number of population, number of iterations also defined. Now, here you see there what we did in the PSO, what we did is we just initialized P best, G best, everything, the velocity, position, everything we initialize, right? Same way, here we have alpha wolf, beta wolf, and the delta wolf. So we have to initialize alpha wolf position, alpha wolf score. Then beta wolf position, beta wolf score, and delta wolf position and delta wolf score. And as I told, this problem is a minimization problem, so I have used infinite. Okay, so once it is done, we have to generate the population position randomly, right? The same equation, you see how the random population is created. You see the position is equal to UB minus LB into rand into LB. The same thing is used here also. You see the position of the wolf, the current position of the wolf is equal to random into LB minus UB. So UB minus LB plus LB. So the same random population position is used. Okay, then after that we just calculated the fitness. Okay, here f object is nothing but the fitness function what we have done already. So here the named as objective function named as. Okay, so we'll be finding the fitness and now I'll enter into the loop. Okay, if my current iteration is less than or equal to maximum iteration, it will go into the loop. So for each population, as I told you, see what we did for each population, we found the fitness. Same thing here, you see, for each population, I'll be finding the fitness. Once after finding the fitness, what we did, we just updated the P best and G best, right? So here in GW, what you have to do, you have to update the alpha position, beta position, and delta position. That's what here you see. The alpha position is updated, beta position is updated and delta position is updated. Okay. The next what we did here, we updated the inertia weight, right? So here what we had to do is we had to update the A vector. So once this is done, what we did here, you see, for each population and for each dimension, velocity and position is calculated. Correct. So now here also you see, for each population, each dimension, we have to find x alpha, that is x1, then x2 and x3. How these are calculated? Based on these equations. You can see based on these equations calculated. X1 is equal to x alpha minus a1 d alpha. X2 is equal to x beta minus a2 d beta. X3 is equal to x del minus a3 to d delta. So based on this, you see that it is calculated. X1, X2, X3 is calculated. Now my final position is nothing but the average of 3. So from this, you can easily compare your PSO algorithm with GW, right? It's almost same, except very few matters, right? So the same way we just created the GW algorithm, then objective function as we created same. Okay, so I just run the algorithm, just see how the algorithm is performing. It's better than the previous algorithm. You can see what I did is the dimension I have taken as 30. So I'll just go with 2. I'll just go with, because for PSO we tested with 2, no, dimension 2. So I'll just run it. You see, it could able to reach 0 value. With 500 iteration itself, it could able to reach a 0 value. You see, the iteration is only 500. 1000 I kept, sorry. I'll just keep 500 also. I just run it. Okay, so it gave about minus 233. Okay, gave about minus 233. I'll just simply improve the population size. You see that it could able to minus 246. So it is not good. Maybe I'll just increase my iteration to 750 and I'll keep the same population size. Okay, you can see that it could able to reach minus 323. So still it is not reaching 0. Maybe if I keep 1000 iteration, maybe it can reach 0 value. See, it has reached to 0. So now suppose if I increase the dimension, you see, I'll just increase my dimension to 10. As you know, for dimension 2, it could able to reach 0 with 1000 iteration. Now same 1000 iteration, you see, I kept my problem dimension is 10, but it cannot reach 0, minus 121. You see, so now again, what I do now, I'll increase my dimension to 30. I run the algorithm. You can see it could able to reach only minus 16. So from this, what I want to conclude is, if the problem dimensions are more, the algorithms are struggling to handle the problems. So you have to create some kind of mechanism to handle high dimension problems. That's what we need. That's what we have to do. Okay, so this is GWO with a simple numerical problem. Now the same GWO algorithm, I'll just use it for my parameter estimation problem also. If I run this, it will give very best result compared to PSO. I'll just show you, you can see. So I just kept, what I kept is 1000 iterations and population size is 30. Okay, so you could see, yeah, fitness, the curve fitness, you can see. The PV curve is this, and IV curve is this. So I could say still somewhat is not matching. Now maybe I can say it's somewhat poor result. So what I do now, I just run once again. I'll try to find the best solution than the previous one. Yes, I think it is better than the previous one. Yes, it's good. Yes, very good result. Okay, compared to the previous one. You see now the curve fitting. The curve fitting is perfect, 100% matching. Your estimated curve and experimental curve is 100% matching. And also just look at it, and also just look at the alpha position. You see, as I told, the benchmark value is 0.7608. You see, it could able to find almost same value. And you see, it could able to find the same current, and it could able to find almost same series resistance and pair resistance. And also you can see the diode ideality factor also is about 1 to 2. So compared to PSO algorithm, this algorithm can able to give the best result for the parameter estimation problem. Okay, and also you can see throughout the iteration how my photocurrent is adjusted. In this, whatever the best current is, that will be shown here. That will be shown in the alpha position. Okay, that will be shown in the best position. Okay. So in this way, everything is, so suppose if you want to see how, how my diode ideality factor is varying throughout my iteration is, I just I just run the simulation again. Okay. You just see how the ideality factor is changing throughout the iteration. Yeah. You can see now, this is diode ideality factor. You can see it start with 1.8. Okay. Then throughout the iteration, it will keep varying. Okay. And will tries to find the best value of the diode ideality factor, and that will be displayed in the best position. Okay. So I hope everything is clear. Okay. So I just want to acknowledge before concluding my session. Okay. So I acknowledge the contents of the other peers whose contents are being used to comprehend the subject better. And I do so solely for academic purposes, not for any commercial purposes. And I do not claim any ownership of any of the contents of other peers. Okay. So with this acknowledgement, I just want to thank you all people for patient listening. Almost 3 hours the session went on. I hope everything went smoothly. Okay. And if you want to discuss with me, you can contact me through my email ID, and the mobile number, the WhatsApp number is also given. You can contact me at any time. Even you can refer some of my papers in my website. It is everything is listed, and a few codes also listed in my website. You can download it and you can use it. Okay. And if you need any clarification or if you want to collaborate with me, you can contact me at any time. Okay. So with this short note, okay, I just hand over the session to you people. If you have any doubts, you please ask me so that I'll just try to clarify the doubts. Then we'll wind up the session. So I hope some questions are there. Yeah.
Okay, thank you so much, Doctor. Doctor, I think there is some questions in the chat
Yeah.
box.
I'm just checking it now. So can PSO and Gray Wolf optimizer to be used to solve the optimal power flow problem? Yes, 100%. Actually, today for today's session, I thought of taking the optimal power flow problem only. Because of the time constraint, because the optimal power flow problem, it will take more time to formulate the objective function. Because we need to take the data, we need to take some kind of IEEE standard data, where then we have to extract the data and we have to connect the data, we have to map the data, and we have to consider the emission coefficients, wall point effects, everything we have to take. So I thought the optimal power flow, if I take minimum 1 hour is required to formulate the objective function alone. So that's why I couldn't able to do it. But 200% you can use PSO and Gray Wolf optimizer. But I tested personally PSO for optimal power flow problem. It couldn't able to converge. Even for IEEE 33 bus also, it couldn't able to converge it. So it's better to try with some good algorithms, so that, or some improved versions of PSO, maybe it will be help you to get the best result for optimal power flow problem. Yes, all these algorithms can be used in MPPT or solar cell application. Yes, actually my PhD area is the MPPT. Personally, I have used GWO, WOA, SAP swarm algorithm for MPPT application. I have published many papers in MPPT application. Yes, it is possible. The only thing is we have to formulate the objective function properly. Once you formulate the objective function, yes, you can use all these algorithms for the MPPT application as well. So what the dimension here refers to in this problem? Yes, the dimension is nothing but number of unknown parameters. Okay, so if we take a single diode model, that there are 5 unknown parameters, right? That photocurrent, the reverse saturation current, diode ideality factor, series resistance, and shunt resistance. These are the parameters to be optimized by the algorithm. So this 5 parameters are the right. This 5 parameters nothing but the problem dimension. Okay, suppose if you take OPF problem, as one of your friends asked, OPF problem. For OPF problem, minimum you have to use 24 dimensions. The problem dimension is 24, because I'll be taking the voltage of all the buses. I'll be taking the reactive power, real power flow of all the buses. So by considering everything, so you'll be having around 24, the minimum number of dimension for OPF problem. But for solar parameter estimation, 5 for single diode model, 7 is for double diode model, and 9 is for triple diode model. Okay, so it's all depends upon how many variables you want to compute using algorithm. That is nothing but the problem dimension. Okay. Yes, can you share the GWF code? Yes, I will share it with you people, so you can take it, just share it. Okay. So can we have the slide? So slide. Okay. So you want the presentation slide? Okay. So I can give you, but so a lot of copyright issues are there, so I cannot share it. But the codes I'll share it with you. You can use it. Okay, because some of the slides are taken from the Syed Ali Mirza Ali. So we have to take a permission from him to share it. Okay. So I cannot share the slides, but I'll share the codes with you people. You can use it for your applications. I think maybe they will be sharing the recordings. Difference between single objective. Yeah, it's a very good question. So difference between single objective and multi-objective optimization. Yes. So I'll take the same problem like one of your friend has to know optimal power flow problem. So in optimal power flow problem, if you take, we have multiple objectives. One, maybe I have to reduce the fuel cost. This is one objective. Okay. Then I want to reduce the fuel cost as well as I want to reduce the emission. Yes, that is your second objective. Okay. Then the third objective, I want to reduce the fuel cost. I want to reduce the emission. Then at the same time, I just want to reduce my active power loss also. So now how many objectives are there? There are 3 objectives. Okay. If you solve the problem with one single objective, then those problems are called a single objective problem. For example, if you consider only fuel cost, and it is single objective algorithm. Or if you consider only emission, it will be a single objective problem. If you consider only the active power loss, again, that will be a single objective problem. But if you consider these 3 simultaneously, and those problems are called multi-objective problems. Okay, so you can use single objective algorithm to solve the multi-objective problem. For that, you can use weighted sum approach. For example, I'll just create the objective function for fuel cost and active power loss and emission. I have 3 objective functions. Okay, now with the help of 3 objective functions, finally I'll be forming one objective function with the help of weighted sum approach. For example, my final objective function is equal to W1 into fuel cost plus W2 into emission plus W3 into my active power loss. So here the W1, W2, W3 is nothing but the weight factors. If we add all 3 weight factors should be equal to 1. So you can play with the W1, W2, W3 values, and you can solve your multi-objective problem with a single objective algorithm also. But if you want to solve the multi-objective problem as a multi-objective, what you have to do is you have to create a multi-objective algorithm. Okay, you have to create a multi-objective algorithm. So we have a lot of multi-objective algorithms. So my present research area is on multi-objective algorithm and many objective algorithms. Multi-objective algorithms can solve up to 3 objectives simultaneously, but many objective algorithms, it can solve even hundreds of objectives simultaneously. That is called many objective algorithm. At present, very few people are working on multi-objective, very few people are working on many objective, but in future, most of the people will work only on the multi-objective and many objective algorithms. So far the people are not having awareness about multi-objective and many objective. Maybe after 2-3 years, the people will work only on multi and many, because most of all our real-time applications are multi-objective applications. I hope it is clear. And can you do another workshop about multi-objective in distributed network? So that's up to you. So we need some more time for that. Yes, we can do it for sure. Yes. It was so good workshop. I hope we can repeat it again, and thanks. Yes, thank you. Thank you. And can you please summarize the meaning of the fitness as it applies to the optimization? So fitness is nothing but your objective function value. Okay, so we have created no objective function is equal to the sum of x square we have created, right? So sum of x square value is nothing but your fitness. Okay, even we have created the fitness function for SD, sorry, your single diode model, right? So the RMSE we created, no, the value of RMSE is nothing but fitness for as a parameter estimation problem. So the fitness is nothing but objective function value. I hope it is clear. So can we get the recorded? Yes, maybe they will share it. I will share the recording. Okay. So can a single diode model can be? Yes, obviously. we can formulate the single diode model as a multi-objective problem also. So that I'm doing it. I submitted a paper already. Okay, it is in revision now. Okay, so maybe in future I'll share it with you. We can create the parameter problem, estimation problem as a multi-objective problem also. Yes, it's possible. Yes, so yeah, I think the questions are over, I think. So yes, I'll share the course. You can use it, or as I told you already, it is already available in my this one. This it is available. Okay. It is available here. I just post it once again. So code is already available for chaotic Jaya algorithm. It is already created and it is done. So only thing is, if you want to use GWO, you keep GW and run it. If you want to run PSO, you just keep PSO algorithm and you run it. So it will work for any kind of algorithms. Is any other questions?
Doctor, I think there was another question. I'm not sure you have answered already or not. Are these algorithms can be used in MPPT for solar cell applications?
Yes, I told because my PhD area is on MPPT. So we can use all these algorithms, whatever the optimization algorithms are there, they can use it for MPPT applications. The only problem with this modern optimization algorithms are, we need so much of computational power, because so far commercially the people are using only Cordova observation and incremental conductance algorithm and it variants of PNO and INC algorithms. Still, it is not commercialized. Optimization algorithm with MPPT applications not commercialized so far because it requires a lot of computational resources. Because a lot of iterations it will be checking. For example, if you keep 10 population and 1,000 iteration, so every time for every change, the function evaluation will be 10 into 1,000 times. So it will take more time for calculating the duty cycle for each and every perturbation. So that's a problem with the modern MPPT techniques. But if we have more comfortable power source, the computational resources are available. Yes, that is possible. You can do it. Maybe for the academic research, you can do. If you have any kind of OpenRT systems or DSpace, you can do this kind of the real-time system. You can do it. It's possible. You can do it.
Is there any questions? You can unmute yourself and then you can ask. Else you can raise your hand. I will unmute you. Is there any questions? If no more questions, then maybe you can take on group photo. Can you please switch on your camera?
So I hope you people enjoyed it. Suppose if you have any doubts, you can contact me at any time. So it's no problem. So
Is there anyone going to join with us? Hi, Shiva. Okay, so I think that's also, I will take on photo. So, okay, I'll be counting 3 to 1. So please keep smiling. Is there anyone going to join? Okay, so I'm counting 3 to 1. So please keep smiling. 1, 2, 3. Okay, all right, thank you. I've already captured the beautiful smile. So later I will share the recording link and also the resources that Dr. had shared. And thank you so much once again for joining us today. And if you have any questions, maybe later you can contact directly to the doctor, Prem Kumar. I hope he will answer. So that,
Yes, sir, thank you very much. So it was a wonderful session. I just enjoyed it personally. So it was a long time. It's a long session. I can say it's a more than 3 hours session. So usually the people go with 1.5 hours or 2 hour session maximum. So it's a 3 hour session. So I just enjoyed it personally. Yes, thank you all for patiently.
thank you so much, Doctor. Actually, more than 3 hours, and everyone is just sitting in front of their laptop. So I hope it will be very beneficial for all of us. And see you again to our next event. I will share our next event details. You can join to our Telegram group for updated info. So that's all from me. So stay safe and thank you. Assalamu alaikum.
Thank you.
Walaikum assalam wa rahmatullah. Thank you, Prof. Thank you, everyone. See you next time, inshallah.
Sure, we'll join. Yes.